this PowerPoint is up on the web, and you can download it. But I just realized in getting a sense of what people know and what people don't know that I need to do a bit of scene setting. So I thought before I start going through the slides, I would try and set the stage for where all this comes from, because it's actually been a quite interesting episode in the development of thermal and statistical physics. So let me just do it the tried and true method that people have been using. The best entry point is, I think, the stuff that David was talking about yesterday. David, the inferentialism. Right? Remember that there's a particular way of thinking about, an inferentialist way of thinking about what the approach to equilibrium looks like when you take the Gibbs approach. Right? You start out with a low entropy state, right, that just occupies a small amount of the phase space. There's a time evolution. It sends out the threads that now fill up the larger phase space. But as long as you know where all those threads are, right, there actually hasn't been any sort of increase of entropy, and so the approach to equilibrium hasn't really happened, or the increase of entropy hasn't really all happened. To get it to happen, you do this coarse graining where you throw away information. You now know less about the system. Right? So in that kind of inferentialist gloss, the approach to equilibrium, the big effect in thermodynamics that entropy increases, is to be understood as a loss of information. You know less about the system than you started with. Right? That's the kind of seminal connection. And the question is, can you do more with that? So let me just write up a few words here that are kind of useful. One is that the increase of entropy equals the loss of information. Fairly loose ideas. That sort of idea was the sort of thing that Brownian in the 1950s tried to pin down a little bit more precisely. And he introduced this idea of a quantitative measure of information, right, that he associated with negative entropy. He called it neg entropy. Now the trigger for a lot of this was that Shannon and Weaver, I guess it was in the late 40s, does anyone remember yeah, Shannon and Weaver had come up with what we now know as information theory, a theory that is of tremendous value and use in communication technology. And they had introduced the same formula for the measure of information as is used by Gibbs. You remember the P log P formula? That integral P log P formula is the same formula that I just write it as P log P because it's the guy that keeps popping up. And so this was sort of hot, exciting stuff. And the idea in the 1950s was that you could somehow incorporate this idea of information into thermodynamics and make the connection that Shannon and Weaver never made. I take it you all know there's the story that Shannon was developing information theory. He found this quantity P log P, and he was trying to figure out what the name for it should be. And was it von Neumann that he ran into von Neumann? And von Neumann said, "Oh, you should call it entropy because the same formula was used in thermodynamics." And I think if I get the line right, and nobody understands it there either. Is it something like that?
He said you should call it entropy for two reasons. One, it's been used, the same quantity has been used by Boltzmann and interpreted as a form of entropy. And second, if you use the word entropy in a debate, you will always win because nobody understands what it means.
Right. So I'm afraid that, in my view, was rather prescient because this marked the beginning of a long series of efforts to get something more. Now, you must understand that, at the initial level, at the level that David was talking, that's fine. I mean, that works terrifically well. I don't have an objection with that kind of gloss. What's driving that analysis is still the statistical physics, right? There's nothing new coming in. But there's this lingering thought that somehow, over and above the thermodynamics, there are ideas about information itself that can be built into thermodynamic theory, and that somehow this is going to be enormously revealing and enormously useful and enormously helpful. So, so the question, the project becomes, can you push the use of information talk beyond the level of comfortable redescription? Right? I mean, there's a superficial level how when we say that increase of entropy is really just a loss of information. I don't mean much more than what you already know. I'm just, I've just broadened the scope of my description to include systems that I formerly knew were not truly the case. Right? So there have been a number of ways of doing this, and I'm going to mention two, and then explain how they came about. One of them is associated with Brownian and Szilard. John Norton and I named this thing. Oops, that's an L. Szilard's principle. Now, you'll see in a moment why this comes about. But the idea is the following. When you do a measurement, you gain information. So if you want to figure out which of two possible states some system is in, you do the measurement, you now have gained one bit of information. Right? The proposal is that one bit of information costs you thermodynamic entropy. Right? I'd say creates thermodynamic entropy, but there's always a little bit of vagueness here. So one bit, so gaining one bit of information, as in a measurement, is the switch in the left or the right position. So we have one bit is associated with S is K log 2. So that was one principle that came in the the 50s was the era of information technologies, and Shannon was hot stuff. Starting in the 60s, yeah.
In this case, did you have equally likely states you're measuring? To be here or to be here, they're both equally likely. Was it any two states? Any two state partition as well?
It's both. We're not dealing with a literature that's so precise that I can really tell you.
But if you're measuring a system which, at least in some ways, you characterize it, if you're measuring a system where your antecedent information about it is that it's probability 0.9 being here and probability 0.1 being here, yeah. The information you gain from that
they'll be different.
A lot less than one.
Yeah. But if you have a system where you don't have probabilities, you just have two, they're still going to have that K log 2. I'm sorry, that's what I meant. Yeah, no, if you have probabilities, then absolutely the probability is going to be half-half, or you don't get that formula.
If I learn that you aren't Elvis, I don't learn one bit, right?
I'm sorry?
If I learn that you aren't Elvis, I don't learn one bit. Intuitively, anyway.
Let me just bracket that. I'm not a practitioner of the theory because I don't find it consistent to practice it. So,
but if you mean one bit in Shannon's sense, then
you better have it. Yeah. But I think there are cases where they don't have probabilities and they still are going to put this here.
It's an abuse of the information theory side.
I'm sorry.
It's abuse of the information theory side of it as well.
Okay. So in the 60s, computing became started to rise. People got very interested in EVERT. And so things to do with computation started to become popular. And a competing research program rose up, which was based on a different information principle. It's one that I will be talking about. And this is Landauer's principle.
Did you guys coin that phrase, or was it already in use?
Landauer, it was in use when we were writing. I don't know when it came about. We certainly coined that one.
I think Bennett coined it.
Yeah, I don't know who first said it. I don't think Landauer. Right. Where this earlier tradition had said that acquiring information is what is associated with the entropy. They say no, acquiring information is not. It's getting rid of it. It's erasure. It's losing information that is associated with entropy creation. And so if you get rid of one bit of information, erased, acquired, is there a C in acquired? Yeah. One bit erased corresponds to S is K log 2. And a point that will be important when I'm speaking later is that part of the research program that built up around Landauer's principle was a negation of this guy here. Right? So they wanted to say this is the only place where you get this entropy effect. These guys just got it wrong. They were mistaken. They're very smart people, very fine. You know, love children, play with animals, but they got this bit wrong. You can acquire information without entropy cost. So how does all this work? Well, the natural home for this turns out to be analyses of Maxwell's demon. So let me go through it. I know Wayne talked about it, but the example is so important that it's really worth seeing it played out in detail. So this is the version of Maxwell's demon that Szilard developed in 1929. This is Szilard's one-molecule engine, and this example has controlled the literature for since 1929. It's the one guy that keeps coming back over and over again, and you'll see the figures I'm about to draw repeated. Here's the basic idea. You start out with a chamber that has a single molecule bouncing around inside. So this is the one molecule gas that Szilard introduced. What you now do is you take a partition, a little wall, a sliding wall that you insert halfway. You do this frictionlessly without any work, all the usual idealization, slide the thing in. And in the process, you're going to slide in. You're going to trap the molecule in just one side. Okay? If you got the thing, without all the standard idealizations, no friction, nothing. You just slide the guy in. The molecule gets trapped in one side. Now, just applying the standard thermodynamic analyses that we've seen before, what you have in effect done is to compress a gas to half its volume. Right? You had a spontaneous compression of the gas. This is an ideal gas. It's a one-molecule ideal gas, but it's an ideal gas. It obeys all the relations of ideal gases, and as a result, the entropy of the system has reduced. Right? The entropy has been reduced by K log 2. Now, what you've just seen there is the sort of thing that people were getting very interested in around the time that fluctuations hit. Einstein, on the strength of the, as I described to you, on the strength of the fluctuations that he saw in Brownian motion, had declared that the second law of thermodynamics is no longer exactly valid when you're dealing with molecular scale systems. Poincaré had been much more figurative, writing in 1904. He'd already accepted that Brownian motion was some kind of a thermal process that was violating the second law. He even said one, I don't remember the exact quote, I'm sorry, I would have dug it out if I realized I was going to speak about it. He said something like, we don't need a Maxwell demon to see the second law reversed, we only need a microscope. Right? And someone...
At that point he was still skeptical about whether that explanation of Brownian motion was correct, and it's all phrased and subjunctive. If that explanation is right, then we'd be seeing, and he actually took that as an objection to, as a reason for skepticism about that explanation, because it's second law. Don't want to get rid of that.
Oh, I didn't know that. That's good. I should go back and look at that again. This was the, okay.
You said Poincaré, right?
Yeah.
Well, maybe you made this remark twice. I do know that in 1893, when he had his recurrence theorem, he wrote, we do not have we do not need to be as agile and observant as Maxwell's demon. All we need is to have a little patience.
Right. And it's meant to
But did
be.
he also write about Brownian?
Yeah,
He said very similar wording about Brownian motions.
Yeah,
If you want it, I can dig up the quotes.
Right, and there it's meant to be a reductio, because it follows, what follows that is, I don't know if the English kinetic theorists have a way out of this contradiction. And what he meant was a contradiction, not internal contradiction, but contradiction with the well-established fact of the second law of thermodynamics.
Okay, so it's standard just to complete the cycle, which I'll do here for you. You've had this spontaneous compression. So people are saying, yeah, but if you really reduce entropy, you return everything to its initial state. It's the standard device in thermodynamic analyses. Return things to their initial state and see what you've got. So what you do is you then expand the gas, right, in a thermodynamically reversible process to raise a weight. Right? The work that you're going to get out of that is kT log 2, and the work that you get out in raising that weight is going to be supplied by heat drawn from the thermal environment. Well, this is an isothermal process, and so you'll have heat of kT log 2 going in. And so the net effect then of the entire cycle is to take heat of kT log 2 and convert it into work, which is a direct violation of the Thomson form of the second law of thermodynamics. Okay, so that's the. Is everyone got it? Because that example is so powerfully important. It's all lurking in everything else that's going to happen.
Just to clarify, when you say Thomson, you're not being to distinguish that from the what would be called Kelvin-versional.
Oh yeah. Sorry. The one that says you can't convert heat to work fully without affecting any other system. Okay, so how do you so what's the response? Well. Everyone in this tradition says, no, you can't have one of these demons, they don't work. Why do they fail? The key moment for people who work in the Szilard tradition, and that's people like Brownian, von Neumann wrote in this as well. The key idea is that in order to do this step, right, you've got to figure out where is the molecule, right? Is it on the left or on the right? You've trapped it with 1 in 2 chance. Is it on the left or is it on the right? You have to find out where it is so that you can hook up the cables that will go to the weight that will then allow the expansion to happen. And where is the molecule? You need 1 bit. Following Szilard's principle, when you acquire 1 bit, right, you have an increase of entropy of plus k log 2, and Reversible dicto, it just cancels perfectly. This k log 2 of the entropy cost of figuring out where the molecule is exactly balances the entropy reduction that you thought you had, and everything works, and there's this tremendous sign, this sense of, oh yeah, great toy example. Right. What happens for the people in the Landauer principle tradition? Well, they say, no, that's not right. You can always figure out where the thing is without entropy cost. Right? But you've got a little guy here, a little demon, a little man who's doing all this work, and he has to remember, where the molecule is. If he doesn't remember where the molecule is, he can't do anything. Right? And in order to complete the cycle, and that is to take everything back to the initial state, the demon has to erase his memory. Right? So, erase 1 bit in the demon memory, and there's the entropy of k log 2 that squares the accounts. That squares the book. Okay, so that's the shape of the literature, and the modern tradition is saying that that this is the way to go. This approach is now so completely standard that you find it in the first-tier journal literature. I just noticed recently that there's a letter to the editor of Nature that just states what I described here as sort of, this is what everybody knows, and then goes on to do some experimental work claiming to have proved Landauer's principle. I mean, my own view of this, for what it's worth, is that we are not in any way better off for this intrusion of, if you want to understand why this thing doesn't work, right? It was actually Marian Smolakowski in 1912 who figured out what the problem was. Now, he didn't apply it to this case because Szilard didn't propose it till 1929, but Smolakowski pointed out that when you're dealing with very tiny systems like this, they are completely buried in fluctuations, and they're so buried in fluctuations that no process that you think goes forward actually does the way you think, and there's almost always a reverse process that undoes everything. I'll just leave that as a general claim. You'll understand much more clearly why I think that fluctuations are the key thing to look at, because that's the basic content of the no-go result that I'll talk about later on.
Presumably, John, that's compatible. The fact that in fact you can never build such a thing in fluctuation may be the result that even in principle you couldn't, is still compatible with that, and I know the principle might be true, which is be able to determine why you couldn't do this.
Yes, that's correct, although I think there's more to say. Yeah. Okay, so now let me pick up where I was going to pick up initially. This is the background, and I want to go more slowly and lay out the thinking behind the Landau principle approach. Okay, so I'm going to, so we're going to imagine that we are involved in practical computer science. We want to build computers, and the difficulty that keeps coming up in building computers is that they generate a lot of heat. This is a really serious practical problem for the design of computers, right? So a bit of history here. I still remember, I was a sentient being in 1985, and lived in awe of the great Cray computers. These were the super fast computers that, that if you could get access to this, you could compute things that nobody else could compute. And the key limit in their design was the dissipation of heat. Right? They generated huge amounts of heat, and this comes from a Cray sales brochure from 1985, and they're describing, they're boasting proudly, in fact, of the system that they use for dissipating heat inside the computer. The computer is literally immersed. I'll read it here, in a cabinet filled with a colorless, odorless, inert fluorocarbon fluid. The fluid is non-toxic and non-flammable and has high dielectric, that is, insulating properties. They mean electrical insulating properties, right? It wouldn't make sense. It also has high thermal stability and outstanding heat transfer properties. The coolant flows through the module circuit boards at a velocity of 1 inch per second and is in direct contact with the integrated circuit packages and power supplies. Right, so the thing is sitting in this current of freon that is, I guess it's freon. That's a commercial.
Which has since been banned.
Yes. Yeah. Well, yes. Yeah. Exactly. And that's what's wrong with it. Now, you're thinking, yeah, that's familiar. Of course, when you make, our chips are like that. This is just the standard design. It's very common to have a little fan sitting on top of the chip. These are vanes that are going to passively draw the heat away. And now this thing here is a heat pipe. I don't know if you've heat pipes are, in the engineering world, they're wonderful devices. It's just a pipe, and inside there's a volatile fluid under its own vapor. Right? There's no air; it's just under its own vapor. And what happens is there's a cyclic process where at the hot end the vapor is the liquid is boiled. The vapor moves along, condenses, and then by capillary action gets sucked back. And so they're very effective means of doing this type of thing. So I'm showing you this just to show you there's a lot of serious technology goes into worrying about how to cool these things. So it's an interesting issue to determine just how much heat has to be has to be generated when you compute? Is there some minimum amount of heat that that always has to be? Well, the first step, the one it's kind of so obvious that people don't talk about it, so I'll just labor it just for a few moments. The key first step is to make things as small as possible. Right? The smaller they are, the less the energy that's being processed, and so in general, the less heat. And that's been the direction. It also speeds things up because the connection times are better. So that goes too big. You want smaller and smaller and smaller, and you just keep going. Every time you make it smaller, it gets better, until you make it as small as you possibly can, and then you're down at molecular scale devices, where the components that you use in this idealized limit are going to be the smallest units possible. So if you can, individual electrons, individual molecules, individual spins, whatever you can get down to, that's the goal that you're trying to reach. And so in that sort of framework, you then ask the question, what is the minimum heat generation? And this is Landauer's principle. This is the text from his 1961 paper, Irreversibility and Heat Generation in the Computing Process. I'm just going to read it to you because they say better the theory than I can. Right? And so he says, in carrying out the restore to one operation, now restore to one is loosely speaking erasure, but the idea is that you have a bit that can have two states, 0 or 1, and when you restore to 1, in other words, you erase, you have a process that will take it from the 0 or 1 state and assuredly give back the 1 state. So in carrying out the restore to 1 operation, we are doing the opposite of thermalization. Thermalization, I might add, is what happens when you have something in a definite state and you open the accessible phase space so it can now move more freely. Right? We start with each bit in one of two states and end up with a well-defined state. Let us view this operation in some detail. Consider a statistical ensemble of bits in thermal equilibrium. If these are all reset to 1, the number of states covered by the ensemble has been cut in half. The entropy, therefore, has been reduced by k log the base e of 2, it's 0.6931 k per bit. The entropy of a closed system, for example, a computer with its own batteries, cannot decrease. Hence, this entropy must appear elsewhere as a heating effect, supplying 0.6931 kt per restored bit to the surroundings. This is, of course, a minimum heating effect, and our method of reasoning gives no guarantee that this minimum is in fact achievable. Right, that's the, yeah?
This is just sort of a broad historical question, which I guess I could have asked at any time over the past 10 minutes or so. Was there, I mean, the Boltzmannian notion of entropy was also around, needless to say, at this, throughout all this development. Nobody noticed that at least on a superficial level, if you evaluated this in terms of Boltzmannian rather than sort of information theoretic notions of entropy, you'd get completely different results and nobody worried about it?
There were many, many things you could have noticed that would have been worrisome and no one remarked on.
I mean, on Penrose with the Markov matter theory, Pittsburgh does a kind of Boltzmannian reconstruction.
But I don't understand. The Boltzmannian reconstruction.
Oliver Penrose.
Boltzmann, yeah, that's only, is that 79?
Okay, David, can you clarify why we get different results if we?
Yeah, you just very trivial scheme. Ask a question: Is there a Hamiltonian you can put on a system? Take some carving up of the phase space into macro states, anyone you want. Ask: Is there a Hamiltonian you can put? Is there a standard? Is there a classically admissible Hamiltonian you can put on that system such that, at least for certain starting macro states, the entropy is very likely to decrease? Answer, for an isolated system, answer trivially yes. Okay? You put a Hamiltonian which is going to take a high entropy macro state, split it up into a whole bunch of microstates whose collective volume is equal to the volume of the original macrostate, but each of whose volumes is smaller, you have a guarantee that the system is going to end up in a macrostate whose entropy is lower than the one that it started out in.
I don't think that distinguishes it from the framework here. To make these assumptions in the Gibbsian framework, you're going to have to require that all of the erasures take any external systems to the same macrostate. Otherwise, this result won't go through.
But
you put that assumption.
Maybe this is so maybe it's sensitive. So I'm supposing, and maybe this is not the right thing to suppose, that the relevant formulation of the second law of thermodynamics here, or a relevant formulation, is there aren't any macroscopic circumstances where the entropy is statistically likely to decrease. Okay, maybe that's not the relevant statement of the second law. If that's the relevant statement of the second law, it's trivial that that's false on the Boltzmannian concept.
Yeah. What I'm saying is that there are auxiliary assumptions here.
Right.
Quite strong auxiliary assumptions. I'm saying if you make those auxiliary assumptions in the Boltzmann case, I think they rule out the entropy reducing machine you're talking about.
Right.
I think.
Right. But let's keep going. There's a long way to go. So. The basic claim is that logically irreversible operations like erasure are going to pass heat or pass entropy to the environment. I'd say the logical irreversibility, which is clearer in other parts of the paper. And then there's the tacit assumption that becomes explicit later on that logically reversible operations, for example, just a switch. If the operation would take a 0 to a 1 and a 1 to a 0, so that the operation can be reversed logically, that they don't have the corresponding entropy or heat creation. Okay, that's the basic idea. Now, what they have in mind here, that's sort of abstract, and you're sort of thinking, yeah, I sort of get it. There is one classic example that makes it all very concrete. Now the first thing is, how do you model a binary memory device? Well, there are many possible binary memory devices. At the time that Landauer was writing, they had little magnetic cores that could have the magnetization going up or down. They were controlled by electric currents. Nowadays, we move little charges around. Either there's a charge in this spot in some semiconductor or not. All of these systems, at a crude level of thermodynamic description, look the same. And they look the same as this example here, a chamber with two parts, with a wall in between, that has a molecule in one side. Right? That's the standard model that's used, and you'll see as we walk through some of this stuff that you get the same sort of thermodynamics out. If you replace that by a more realistic magnetic or electric system. So the binary memory device looks like this. The molecule is trapped either on the left or the right, and so here are the two possible states that the system can have. The erasure process then follows through the steps that I'll now indicate. The next step is to thermalize. You want to be able to just apply one process to both states. So you open a door here, or you pull the partition out. Right? This is the thermalization step that uses that word that Landauer used earlier on. So now you have the molecule has access to both sides of the chamber. Right? Next, you do exactly the sort of reversible compression that we described over here. Right? You then compress the one molecule gas reversibly back to its initial state. Heat of K log 2 gets passed to the environment. There's an increase of entropy of K log 2 of K log 2 in the environment. Okay, that's the when people talk about erasure in this literature, almost invariably that's the process they have in mind, and that's the process that they'll calculate when they're doing the calculations. So how does it all fit together? Well, there are a number of different ideas here, all of which point in the direction of the Landauer principle. I pull out three ideas, right? And I say make this plausible. So the first idea is a pretty straightforward one, and that is here's a credible erasure procedure that everyone talks about, and it does indeed create k log 2 of heat. It does indeed create KT log 2 of heat, that is k log 2 of entropy, and okay, so that fits. Then there's the second argument, which is one that Landauer's text already had in it. There's an idea that we're doing a compression. Right? When you erase, right, you start out with an initial state that's sort of spread over two states, 0 and 1. Right? And when you're finished, you've got that compressed down to 1. And of course, we know that when you do 2 to 1 compressions, right, you have entropy changes of k log 2. Right? So that sounds pretty right. And then finally, there's the information entropy formula, the Shannon formula. If you assume, if you assume that the probabilities of these things are a half, you can then apply the Shannon formula, and once again you get an entropy change of k log 2. So those are the, that's kind of a sort of a muddy plausibility hand wave that says, yeah, it's sketchy, but okay. Over the last 50, 60 years, someone's worked out the details, right? So let's move on. Just looking around the literature, in 2003, Bennett gave what seems to have become the canonical statement of Landauer's principle, just in terms of what seems to get cited. This seems to be routinely trotted out as what the Landauer principle says. And so let me read it to you. Landauer's principle, often regarded as the basic principle of the thermodynamics of information processing, holds that any logically irreversible manipulation of information, such as the erasure of a bit or the merging of two computational paths, must be accompanied by a corresponding entropy increase in the non-information bearing degrees of freedom of the information processing apparatus or its environment. So logically irreversible process such as erasure, things that map two states to one at the level of logical description, will be implemented by something that passes entropy to the environment. And then there's what I've taken to call now the converse Landauer principle. And he says, conversely, it is generally accepted that any logically reversible transformation of information can in principle be accomplished by an appropriate physical mechanism operating in a thermodynamically reversible manner. So if you have logically reversible operations, a bit flip, so 0 goes to 1, 1 goes to 0, that can be carried out in principle by a thermodynamically reversible process. Okay, so now I just want to look at this again and say there's a kind of oddness to this that you should observe. And it reflects a difficulty that I've always felt, and people that I see in people I read. It's actually quite difficult to say exactly what the principle is, because there are actually multiple versions floating around. And you'll see this here, because Bennett actually has, I think, one of the most tangled versions. So let me go through and see. It's not as simple as it looks. You have to be careful about how you say it. And I've been studiously careful to use vague words. So let me just point out what's happening here. This, down here, we're contrasting two cases, and this one is the thermodynamically reversible case. This one you would then kind of expect to be the irreversible case, but it's not. It's the pass entropy to the environment case. Why isn't that the irreversible case? All right. So let me press that a little. There's a kind of some people will present it this way, right? But it's not the canonical version, right? There's a what you would like to say is logically reversible operations are going to be implemented by thermodynamically reversible processes. Logically irreversible operations are going to be implemented by thermodynamically irreversible processes, and then you'll have KT log 2 per bit, right? That's what you would kind of expect. But it's actually absolutely what you don't get. You have to dig a bit to find it. But when you go digging, this is what you find. This is Bennett. He's written this in a few places. This is the clearest example. And again, I'll just read it out to you because he'll say it better than I can convey it. When truly random data, for example, a bit equally likely to be 0 or 1, is erased, the entropy increase of the surroundings is compensated by an entropy decrease of the data. So the operation as a whole is thermodynamically reversible. Right? In computations, logically irreversible operations are usually applied to non-random data deterministically generated by the computation. When erasure is applied to such data, the entropy increase of the environment is not compensated by an entropy decrease of the data, and the operation is thermodynamically irreversible. Okay, so I'm trying to get my head around this. It's saying random data, you erase that, no entropy is created. Known data, entropy is created. I keep looking at that and I keep saying, no, wait, no, don't you have that the wrong way round? Shouldn't it be the other way? No, he's you know, I mean, why might you think it ought to go the other way? Well, let's just think about it informally. Let's say you've got an erasure procedure that's going to work on known data, right? On this case here, an erasure procedure that's being fed known data. Now, either the procedure is going to use the fact that it's known data or not. If it's using the fact that it's known data, it ought to be pretty straightforward just to rearrange things without any dissipative effects whatever, right? I mean, if you've got to erase something, you know, that's in a 0 state that has to go to 1, and you know it's in a 0 state, you just move it to 1, right? So that ought to be the case of no dissipation, but it's not. It's the other way around. But what happens if you aren't going to use the fact that it's known data? Right? Well, then your procedure ought not to make any difference between these two. Whatever happens in the one case should happen in the other. Yeah?
But John, surely from Bennett's conception of entropy, the difference is that the random data has high entropy and known data has zero entropy.
I'll get to it. Yeah, that's exactly right. But I still think it's odd. And you know, what I'm trying to show is that the principle is nowhere near as simple as people would like. You've got these nasty little complications in there that don't. Oh, I'm sorry. Sorry, Ross.
I agree completely that it's hard, but what I puzzled somewhere else, I guess. What you want to do if you want to argue for a principle is at least show some connection between thermodynamic quantities like thermodynamic entropy and cycles, and then quantities associated with information. But you cannot presuppose in establishing such a thing that whatever you call entropy of the data, which is the information sets, to have thermodynamical relevance. But what he's saying is, in order to establish whether the operation as a whole is thermodynamically reversible, in order to draw that conclusion, he simply adds the entropy increase of the surroundings, which is a thermodynamic quantity,
Yes.
by the entropy decrease of the data.
I will say more about that, but
Good.
Yes, my sympathies are with what you said. So there's more coming. Okay, so now this is all. Yeah.
Oh, just a very quick question. When you erase data, your first case from the previous slide, say if you. No, sorry.
Okay. We'll just imagine you can see it still. Yeah.
If it does not use what is known, erasure is just rearrangement. But if you've got a string like 0, 1, 1, 0, 0, 1, 1, 1, and you erase it, don't you turn them all to zeros or all to ones?
Yes, correct.
So that's not just rearrangement, right? You're setting everything to the same final state, so it's many to one.
Well, I guess the difficulty is understanding what's meant by known. If it's known, then no matter how complicated it is, somehow that information is there to be used. Let me just raise this as a question. I'm in the awkward position of presenting ideas of a theory that I myself don't really know how to work, because in my bones I don't think it can be worked. So yeah, which makes me a less sympathetic expositor than I could be. So let me move on. This is what I'll be talking about. This is what's going to come. There are two parts. I'm going to go through the various ways that one seeks to demonstrate Landauer's principle, and I'm going to indicate that I think all of them are flawed, I think all of them are not done well. That is compatible, and that's at the level of complaining and griping. That what I want you to see is that there's a literature out there that moves much, much faster, right, than it should. That the conclusions it's coming up with are simply not warranted by the things that it fairly confidently asserts. Right? All of this is still compatible with the Landau principle still being true. It's just one of these things for which no one has an adequate proof. But the thing that I really care about is this, right? What I'm going to be arguing with this no-go result is that the framework assumed, the complete framework assumed, is a kind of fantasy physics which just doesn't map onto reality. And so that the results that are derived there are not about the world. They're about this fantasy scenario in which, very briefly put, there are no fluctuations. Or rather, there are only some fluctuations that you want to think about and you want to ignore the rest. That's where it's ultimately going to go. So let me go through the first part and then we'll take it from there. Oh, yeah, look at that. So I gave you three plausibility notions that are used, and so let me go through them again. The first was that when you look at this plausible system for erasure, right, you do indeed get the result. I've had to work through a lot of derivations of Landauer's principle, and this is probably the most common derivation amongst those that do elaborate calculations. What they do is they set up some version of this erasure procedure that we just talked about, and they calculate, and the outcome's this result at the end. But if you're not paying attention, you don't realise that it all depends on just one move that is questionable. So this was the erasure procedure that I showed you before. You start out with a system that might be in one or other of these two states. You don't know which, so this is an either-or. The system is one of those, so you don't know which. Then what you do is you remove the partition to thermalize. You now have the molecule can access the entire space. You do the compression, you get the K log T out. And of course, the key move, the moment in the whole proof, is this thermalization step. The idea is that the entropy somehow comes from erasure, whereas when I look at it, it comes from the fact that you've decided to build in a thermodynamically irreversible process. If you have a gas that's trapped in one side of a chamber and you pull out the partition, you have an irreversible expansion that creates entropy, whether it's one molecule or 10 to the 23 molecules. Now, this one move, I said that procedure is important. This one move is the thing that I see repeat endlessly in these in these derivations. So that's where the entropy is coming from inside the argument, and so so as I say here, the proof only shows that an inefficiently designed erasure procedure creates entropy. There's certainly no demonstration that all possible erasure procedures must. And this is just a flat-out logical flaw in the standard proofs that you find in the literature. Now,
Let me leave you about to make that point, so let me delay the questions for it.
Sure. Okay, but there's a comeback that says, but look, we want our procedure to work on arbitrary data, so mustn't we thermalize in order to be able to work on arbitrary data? Well, at this point, I'm sort of a little lost because I don't really know what the rules of the game are. We're dealing with a kind of a fantasy ontology of what things can be done at the micro scale and what things can't be done at the micro scale. So as far as I can tell, no, if I just play by the same rules that everyone else is playing by, it seems to me to be perfectly reasonable to say, no, there are other erasure procedures that don't have this step in it, right? And let me show you what they look like. So here's one. Supposedly, I mean, this was the big deal that came out of the Landauer principle analysis. Supposedly, I can detect which side of the chamber has the molecule by some process that doesn't create entropy. And I can also just do a shift operation where I just move this guy over, you know, without creating any entropy. These are two primitive processes that are routinely used. So I just put the two of these guys together, right? And so, you know, I look at my device, I detect whether or not it's in the reset state. If it is, I do nothing, and if it isn't, I move it over. Or here's an even simpler one. I look at my device, right? If it's in the reset state, fine. If it's not in the reset state, I pull out the partition and put it back in again. And I check, is it in the reset state? And I just keep doing that. It doesn't take many repetitions of that to have a ratio with very high probability. Now, that's the beginning of the debate, but, you know.
You haven't erased them because you know which side it was in. If you learn what side the bit was, the bit's moved from the device to your head.
Yeah, and that's where it goes next. Yeah, I know. But now, all right, I'll just keep going because I don't think any of this actually works. I think it's highly.
Can I just ask a question about previous
Sure.
slide? So,
Yeah.
so on the notion, I mean, it's clear in the situation if you want to keep track of, say, when the Boltzmann entropy increases, then you're dead right. But a lot of the notion of entropy that's in play here is one, giving the Gibbs entropy, and two, is going to make no distinction between different notions of probability. So if your starting assumption is that the system is on the left with probability half, and on the right with probability half, then removing the partition doesn't change the entropy at all.
You'd have to go back to the beginning and say all that again.
Okay. So if I'm using the Gibbs entropy, and if I'm not making any distinction between different kinds of probability of play,
Yeah,
it's all
well,
entropy. Yeah, sure, but these guys aren't.
Yeah, and that's why I think they're mistaken.
Right, but then the
Well,
mistake
hang
is
on,
what's subtle.
I think that's coming up now. Yeah, no, I think that's coming. That's,
But it's controversial whether removing the partition is entropy increases the entropy.
I'll be saying more about it, so let's maybe pick it up after I say more. Okay, anticipationless erasure. Okay, the one that's pertinent is number 3, so just this will be a bit of dead time or perhaps further material for you, I'm not sure which. Okay, there's this many-one argument that says that when you compress, oh no, I think it might be here. That when you compress, when you erase data, you're compressing the phase space. And so the idea, this is, you remember Landauer talked about an ensemble. This is the ensemble of random data. You've got some left and some right. This is random. It occupies twice the space of the reset data with everything moved over to the left. And so there you have the 2-to-1 compression. Erasure halves the phase volume, so erasure reduces the entropy of memory by KL2 per bit, and so entropy of KL2 must be passed to the surroundings. That's the argument. I just think it's wrong. It's based on a false premise. Random data just doesn't occupy twice the phase volume. I mean, to count them up, there, of all the cells here, there are as many occupied cells in the reset data as there are in the random data. It's just been misdescribed, right? It's being misdescribed in a way that would conflate it with formalized data. This is down here. Now that occupies twice the volume of phase space. Okay, getting there.
Yeah, and I'm just going to keep making irritating interruptions. Maybe I'll just be quiet until after that.
Sure, whichever, I don't mind. Well, unless it goes on too long. Okay, so this is now the thing that you talked about. One of the things that's going on here, and I'll say maybe a little bit more about this, is that these people are actually involved in a redefinition of standard thermodynamic terms. Right? They're actually beginning, and certainly not completing, a rebuilding of thermodynamics. And so here they have redefined the word reversible, or what a reversible process is, to include the following case. I think this might have been the one that you were referring to. Let's say that we have random data here, right? and we have thermalized data down here. Right? It is the case that if you insert a partition in the thermalized data, you'll get back to random data. There'll be different occupations, but the frequencies are going to, near enough come out to be the same. And then you can go back down to the thermalized data by lifting the partition. So what they say is, we now have a thermodynamically reversible process in which you lift the partition, you put it back in, you lift it, you put it back in. You can go, there's no heat passing between the environment, so it's adiabatic, and you can go backwards and forwards as many times as you like. Therefore, it's reversible. Now that is what is behind Bennett's earlier idea that if you erase random data, right, you're going to pass entropy of the environment. Right? This is the point that you made. This is exactly why he's saying it. It's because he's redefined the word reversible here. Now, I just tell you, we have results elsewhere in thermodynamics that just tell us that if you just take one of these guys, pull out the partition, right? You've had an irreversible expansion that is creating k log 2 of entropy, right? I mean, that result hasn't now gone away. Yeah.
I take it the thought is something like, if I'm not distinguishing between particle being left and particle being right, then in the boxes on the top, what I'm effectively doing is saying, oh, the particle's somewhere in the box. There happens to be a partition in the middle of the box, but whatever, I don't care which side of that partition the particle's winding up on. So, when I take the partition out, that's not like a dual expansion, where I start out very explicitly with the gas on one side of the box and let it expand over to the other.
That's right, and they have a quantity of entropy that they're attaching to that. But this will be the number 3 that I'll get to in a moment. The question is that quantity of entropy doing everything you want? And I'm going to say no, it's not. But let me just finish here. If you accept that as a reversible process, then entropy ceases to be a state function, right? Because you can now set up a very simple cycle around which you have a net increase of entropy. Right? That is where should we start? We'll start here with the thermalized data. We'll stick in the partition, right? Then we'll do which is a zero entropy change process by the presumption, right? Then we'll do the reversible expansion, and you will get the change of entropy of k log 2. So going around that cycle of all reversible processes, you don't get zero entropy change.
But they won't allow that process as a legal process because your choices have to do with the static and thermal expansion, whilst your information on the left-hand data.
Yeah.
It's not, you can criticize that framework, but it's not an eternal consistency.
Yeah, I know that's what they say. I just don't buy it. Everything always moves off somewhere else. Anyway, all right, I'll leave it there. This is the debate that's ongoing.
What is the status of Szilard's principle at this stage of the argument?
Szilard's principle has gone, by presumption, it's false, according to the Landauer Bennett. Yeah, you can do that dissipation. All right, so now then finally we get the information theoretic entropy, the P log P case. The idea is very appealing, and that is you have random data where we now do indeed have probabilities, and the probability of being on the left or being on the right is a half. You compute with the Shannon formula, right? For information, you get. I put in k just as an arbitrary constant. If you're using the Shannon's formula, k doesn't have molecular significance, but that's by the by. The random data will have that information theoretic entropy. The reset data, when you do the sums, will have zero information entropy. Now, this was your concern. That's one sort of entropy. Is it the right sort of entropy? No, it's the wrong sort of entropy. The one thing that they're very clear about in this literature is that the entropy changes they're talking about have to be associated with changes in heat, with heat being passed to the environment and the like. And you just don't get that in this particular case with that sort of over that sort of entropy. If you think about it sort of in an intuitive sense, just not knowing where something is, connecting that up to heat is going to be a bit of a tall order. And you certainly can't just assume that if I write P log P for my not knowing where something is, that I've now made a connection to heat of the type that conforms with the Clausius formula. So yeah.
But one could already make that same argument with the thermodynamic entropy of mixing. That's not related to heat exchange. It's merely involved with removing partitions.
I don't know where that goes.
And it's a certain similarity that it illustrates that because the entropy is lower, it so turns out if I had access to a certain manipulation, and if I knew I had access to it, then I could do something with it.
Okay. Right. So, but let me just go through here. What does it take? So I worked through this one pretty carefully. So what does it take for this formula P log P to connect up with the thermodynamic entropy of Clausius? It's the standard fare in the Gibbs-style formalism. I learned it first just working through Einstein's derivation of it. The key, so you're going to have a region of phase space over which the probability extends. And the key thing is that the system point has access to everywhere in the region. Now that's an essential part of the proof in the Gibbs-style development that the formula P log P goes with thermodynamic entropy. The way it happens is, I think you or who was talking about the Gibbs-style approach. You know the way it works. You calculate the work that's done associated with particularly free energy change, and then the heat is what's left over. But in that when you change the generalized parameters that are going to correspond to to working on the system, the formula only comes out right if over time the system point can visit all parts of the phase space. And of course, so that's the critical condition if you want the P log P to connect up with the Clausius heat formula. And that's exactly what you don't have. If your probability is telling you that you don't know which side of the chamber it's on. Look, this is a messy calculations to do. If you want to read my effort to do them as clearly as possible, this was that paper, Eaters of the Lotus, that somebody actually
What you're referring to, though, is the ergodic hypothesis. That the system will visit all these regions of phase.
Yeah.
That's not part of Gibbs, but it's part of...
It's used in the calculation. If you don't have that, you can't...
Just to the strength of the proof you're stating, are you saying that's given in the... you can prove that there is no way of doing probability distribution other than that?
Well, when I worked through it, if you try and attribute it to that, again, it was a long and messy paper, and there are appendices and things, but that was my understanding of the upshot of it.
So, for instance, the microeconomic distribution.
I don't know. That I don't know because the setup's different. You've got to be in communication with the heat path. It's part of one of the assumptions of the setup.
I'm not really sympathetic to this whole approach, but I have an inkling of what the sort of thing that these people are going to say. I mean, if you take all these probabilities, if you take a thoroughgoing inferential approach to this whole thing, and all these probabilities are supposed to be epistemic, and heat really is just me losing track of stuff, and then it's accessible would probably mean epistemically possible. Then counts as accessible if I don't know it's not in that region.
But then the calculation doesn't work. That was the case I sweated through for the 2005 paper. Just not knowing it's there doesn't give you the term you need in the formula. Yeah, okay, all right. So let me move on. What is needed here really is a rebuilding of thermodynamics using redefined terms. Right? I don't preclude the possibility that can be done. I know of one attempt that I respect, that I think has tried really hard to do it, and I think had the greatest chance of succeeding if any did. And this has been the work that James Lederman and his colleagues have done in 2005. They employ an indirect strategy. The basic structure of the proof is to find some process that's known to reduce entropy. For example, sticking a partition in a wall to divide a chamber that has a one molecule gas in it, and then they're going to couple that to some arbitrary erasure process, any erasure process that you like. That's where the generality comes from. The indirectness then gives you the generality. And then they're going to invoke, they're going to assume it's a key assumption, which it's an assumption, and I don't know quite how you would justify that the second law of thermodynamics is going to hold on average, and so then, because you have an entropy reduction here, on average you must have an entropy increase over there. Now, I'll tell you right now, it's a messy, complicated debate, and I didn't load all the turnings into working memory, so I'm hoping I don't have to talk about it in great detail, because I don't remember how all the details went. I will tell you this much: it's an ongoing debate. James has written stuff. I've written a reply. So it is unfolding as we speak. I understand he has another paper in the works, and I don't know. I'll wait and I'll see what comes out. I'm not confident. I'll just tell you briefly what I've given all the references here, so you can chase it down if you want. Although they're obviously not terribly hard to find. So my concerns are, I've got three of them. The first is they are assuming an inventory of primitive processes that you can combine together in all sorts of different ways as you please. And I find the game very hard to play because I never quite know what's in the inventory and what isn't in the inventory, because you have to learn it by watching what they do and saying, oh, I see you did this over here, so that means now I can do that, right? And so if I work their inventory, I think I end up with contradictions of the statistical form of the second law. They, of course, dispute that. I think that their inventory has all sorts of artificial restrictions. In particular, they're restricting what can be done to what they call controlled operations. Both of these are kind of, grumbling about, oh, I don't think you've set up your system very well, blah, blah, blah. The one that I think is really fatal is the no-go result that I'll get to later on. The reason that I'm unable to get clear on what the inventory of processes are that they're using is because the entirety of it is fantasy physics. It is not map on it. These are not processes that could be found in the world. They are arbitrary creations that enable you to set up a fictitious system, essentially because they're neglecting fluctuations. That's the basic line. But I'll just mention one because it has a nice graphic. They have this idea of a controlled operation. So if I have an operation where I'm going to move this to this, then my machine has to have, you have to anthropomorphize the machine that's doing it and imagine that it has a little memory. Right, and that's just a rule they have. I don't quite know where it comes from. And there's a control bit that says do this as opposed to do that. And they have this principle that a controlled operation cannot act on its own control bit. Right, and as far as I can tell, they take this to be a principle of logic. Right, and so I just want to show you this. This is something in an art gallery. It's a suitcase that's normally closed, and there's a little lever here on the front. And so let me show you what happens when you push the lever in, the little hand comes out and pushes it out again. So the lever is the control bit, and the process acts on its own control bit. So I don't know. One interesting sidelight, I've been talking to James about this, and so I'm saying to him, you're trying to rebuild thermodynamics, it's a big job, how are you going to, blah, blah, blah. And he says, no, this is all just ordinary thermodynamics, and I don't understand why he thinks that. Because if you halve the volume of the gas, you've reduced its entropy of an ideal gas, you've reduced its entropy by K-log 2, and he doesn't think that. I now want to just talk briefly. I want to advertise other work that I've done elsewhere without going through the details. But it's a neglected part.
say on the control and target, and I took the logic there, maybe not in James' paper, but generally not as a matter of logic, as a matter of having phase space conserving dynamical processes. I mean, in the discrete case, one dynamical processes. So do you assume that's your input for right physics?
Yeah, maybe, but there are some steps to be made.
I know, sure, but I mean, that's my impression at the starting point, and the starting point is not intended a priori.
But, yeah, I don't recall them running that argument, but maybe it's one they could. Okay, so one of the things that that's talked about very little is the so-called, is what I call the converse Landauer principle. I read you Bennett's statement of it, and that's the idea that if you have logically reversible operations, bit flips and everything else like that, generalized as far as you like, then they can be carried out in general by thermodynamically reversible processes, if only you're clever enough and smart enough. There's actually very little literature on that. But there is one core argument that seems to be trotted out as the proof. And yeah, frankly, there's a level of ingenuity here that I find really quite extraordinary. And so even though I'm going to grumble about it, I do want to tell you, there's something really admirable in the ingenuity of producing that. I was really impressed. Okay, so this is Bennett's notion of Brownian computation. So here's the idea. He has designed a Turing machine out of idealized components that you find in classical physics. Okay, it's the only components that are allowed are pieces that slide backwards and forwards, or turn frictionlessly in channels, or have their motion obstructed by something, right? And they can only just slide through, but it's frictionless. There are no springs, for example, nothing like that. And it's a very elaborate device. I've shown how it works here. This is his picture. You've got a disk here that'll turn. You've got a head that moves in and out. You've got pieces that come up and down. This is an E-shaped piece. And you can move the E-shaped piece up or down as a memory device. You store one bit that way and the opposite that way, right? And so if there's a gap, you can then move that up and down. And if there's no gap, the thing's locked. Now imagine designing a complete Turing machine using devices like that. Well, he's gotten a long way towards doing that. Not all the pieces are there, and okay, I can ask for more, but boy, there comes a point when you begin to see, yeah, he's probably going to get there, but it would take a very long time. All right, so all of that is admirable. Now how does it work? Well, the whole system is set up so that you have this enormous phase space that gives you the configurations of the state. And the only accessible parts are a single linear channel that goes all the way through that. Right? Such that as you proceed along the channel, right, the various steps of the Turing computation are going to be carried out. You get the idea? Now, what drives it? What drives it is thermal fluctuations. Right? So the system is just rattling a little bit. And the rattles will gradually move it along this channel, and then move it back, and then move it along the channel a bit more, and then move it back, and then move it along the channel some more, and then, and with patience. We're dealing with idealized examples in thermodynamics. When if you're trying to implement a thermodynamically reversible process, then time is the one thing you have as much of as you want, as long as it's finite. All right? And then eventually, if ever the thing gets to the end, there's one step that is highly dissipative that traps the system in its final state. So there's one moment of dissipation in the whole deal. And so he says that one moment of dissipation is just averaged out over everything. And bingo, there you have it. You have a thermodynamically reversible computation. But, because of the linearity of the channel, it's you're doing one stuff. If it were many one, then you'd have branches, and the branches would take even more time. And he says, no, there comes a point when he's not willing to wait anymore. Okay, so it's kind of cute, and I'd never looked at this because it's very complicated, and I just figured he's probably got it right. And in particular, the details of the Brownian computer are quite intimidating to look at. But I did it. I sat down and looked, and then I started looking at the thermodynamics of it, and it's just wrong. It turns out that thermodynamically speaking, the operation of that device is simply the thermodynamic analog of the uncontrolled expansion of a one-molecule gas. So the motions that I described is just what happens if you would start out with a gas trapped in one side of a larger, one-molecule gas trapped in one side of a chamber, and then release the guy and set him loose. The fact that the channel is really complicated doesn't make any difference to it. So it's actually not thermodynamically reversible after all. So anyway, so that's it. All right. I thought now would be a good time to take a break because I'll do the or questions.
What does Bennett say?
I sent him the paper, and he hasn't said anything. So I don't know. He did reply to the Eaters paper. Well, never mind. But that was can I say that was inconclusive? Yeah. It wasn't in print. He sent someone else to do a presentation on his behalf. From what I could see of the presentation,
So just check. So with the Brownian computation, I just didn't follow the step that said this Brownian computation process.
Just slow down a little.
Sorry, I just didn't quite follow the step that said this Brownian computation is supposed to be an example of a logically and thermodynamically reversible process. Just good. Sorry, so is the step at the end where you, the highly anticipative step, is that meant to be part of the computation? Because that seems like a very straightforward reason to think that it wouldn't be.
Oh yeah, no, but the idea there is that you've done very many computations, and then you have this little bit of dissipation at the end, and so if you average it out over everything else, it's small enough not to bother with. That was the argument. And I don't take issue with that. That's fine with me. It's the characterization of this thing as a thermodynamically reversible process. Now, the argument seems to be that at any moment, if you just look at its operation at any moment, it can, with equal facility, go forwards or backwards. Right? And that's a kind of mechanical reversibility, but it's the same sort of mechanical reversibility that many systems have, that is not the same as thermodynamic reversibility. Now, it's not good, the thermodynamic analysis. Another problem is that all of he actually unnecessarily introduces an energy gradient in order to hurry things along, which is entirely unnecessary, because if you're trying to do a thermodynamic reversible process, it can take as slow as it likes, and you're better off making it slow. He introduces an energy gradient and sort of reports results. He doesn't show calculations, but reports results on the energy gradient. The trouble is, you shouldn't use an energy gradient in the thermodynamic calculations. You've got to use a free energy gradient, because the free energy gradient is actually a surrogate for entropy. And so the thermodynamic analysis is just so far from what it should be.
Can I also ask a question about, the criterion of allowing, so as much time as you want seems strange insofar as there's thermodynamically irreversible processes that would count as reversible if we give them enough time, like free expansion. So just thinking, the worry is something like, usually you take a free expansion to be irreversible, but if I pull the partition out, let it expand, and then wait long enough, then like a recurrence theorem suggests that it's going to at some point put itself back in the left-hand side.
Yeah, just hold the thought. The fact that something can return back to its initial state means that it's reversible in one sense, but it's not reversible in the sense of a thermodynamically reversible process, such as enters into the definition, the Clausius definition of entropy. There the condition is that all driving forces are, at perfect balance or very, very slightly removed from it. If you release a gas and then wait for it to come back, you've got nothing that looks like that at all. Okay, I'll be saying more about this because there's this is one of the issues. I didn't realize until recently that there's not univocal agreement on what counts as a thermodynamically reversible process.
If I had to guess, my guess would be that Bennett's definition would be that trace row log rho stays constant. Does it satisfy that condition?
Okay. You mean the Brownian computation?
Yeah.
top of my head. I doubt it, but I don't know.
That would, I mean, just in terms of the internal structure of literature, that would be my strong guess of what he would see as there.
I don't think Bennett has a really good grip on thermodynamics. Should we take a break? It's just me talking as it all left off. The first part that I talked about is largely negative. I'm spending time indicating why I'm not convinced that the framework as it is defined works well. One of the major problems is that I don't know what the primitive processes are. There are all sorts of assumptions about what the primitive processes are, including a lot of anthropomorphizing. So if I'm going to, if I'm going to have this process where I detect, right, where the molecule is, and then do something according to that, I am now constrained to imagine a homunculus that somehow has to keep a memory, etc., etc., etc. Whereas there are all sorts of ways of getting these processes to work where the anthropomorphizing move just can't be worked. The extreme example, which I've written about in other places, is that this form of the Maxwell demon is the one that lends itself readily to anthropomorphizing. Up until then, the sorts of demons that were in the fluctuation literature following 1905 simply had no anthropomorphizing going on at all. They were just processes. The classic example is the Smolakowski trapdoor. You guys know the Smolakowski trapdoor? It's one of a large set of examples. This is due to Smolakowski, and the idea is the following: you have a gas in a chamber, and there's the gas is on either side of the dividing wall, and there's a little flapper here that can move only one way. It can flap open to one side only. Right? You get the idea. Now the design, right? The intended operation is that a fast-moving molecule coming from this side will hit the flap and lift it and form inside here, right? Whereas a fast-moving molecule, in fact, any molecule coming from this side, will snap the guy shut, right? And so then the idea is that this is a very simple mechanical contrivance that does exactly what Maxwell does, near enough what Maxwell's was it something cited, a neat-fingered beam. What was the something?
Neat-fingered and very observant.
Okay, that does it. Now, this of course is exactly the kind of Maxwell demon setup that one might imagine, and Smolakowski can point out it's not going to work because this little flapper here is itself a thermal system. It has to be very light if a collision with a molecule is going to pop it open. And as a result, it's going to have its own thermal degrees of freedom. So it's going to be flapping up and down and in and out, and as a result, the thing will just fail to operate as intended. You might have seen Feynman's ratchet and Paul device. Those of you who have seen it, that's also one of Smolakowski's. Right? Feynman took it from Smolakowski.
Wow, did he know about it? Did he read it there?
I don't know. I find it very striking that exactly the same guy pops up there.
Right.
Yeah.
Right.
So I don't know. He might. Szilard certainly knew a lot of Smolakowski. In fact, if you read the translation of the 1929 Szilard paper, there's a short quote from Smolakowski and then a long commentary. It turns out that the long commentary is actually part of the Smolakowski quote. And when they did the translation, they closed the quote.
But look, the thing that's all of the schemes one has, all of the Hamiltonians one can write down for sort of reducing the Boltzmann entropy are really different from this in a really important sense. They all have what you might call, it's a feature of all of them that the final macro state of the system depends on details of its microstate. Okay, that is, that it has a kind of microscopic sensitivity that eventually gets that eventually gets translated to the macro level, which isn't characteristic of examples like this and isn't characteristic of ratchet and fall kinds of devices and so on. So there's a reason to think that examples like this aren't going to be fully general or definitive.
Can I leave that as a comment and just proceed, because I want to go in another direction with this. I simply want to remark that the sort of micro level operations that are being talked about in this literature can be affected without the homunculus idea that there's a little guy with a memory.
But that's just what I'm saying doesn't seem to be true.
Then I'm not seeing how you get to that. Do you mind if we leave it? I'm sorry, I'm not making a connection, but I'm realizing I'm just getting far afield from where I wanted to go. Okay, the only thing I want to take out of this is fluctuations matter, and the idea here that that Smolakowski observed correctly, that door is going to flap around wildly, and that matters a hell of a lot. That's the inspiration for everything that's about to happen. Okay, so let me give you some examples, right, of what I have in mind, and then I'll go to the general result. So let me give you some examples because they're quite physical. So let's take what is maybe the most common, well-defined process in the whole operation, and that is an isothermal reversible expansion of a one-molecule gas. Okay, this is the thing. This is the one process that happens over and over and over again. Let's look in detail at how we might try to implement such a thing. Remember, the key thing about a thermodynamically reversible process is that it consists of a sequence of equilibrium states, or states as close to equilibrium as you can get them. So all forces are as close to balanced as you can get them. All thermodynamic forces are as close to balanced as you get them. All temperature differences are as small as you like. Any pressure is exactly balanced by an opposing force, and so on for the generalized forces that you find in the thermodynamics treatises. So here's a scheme for doing that reversible expansion, thermodynamically reversible expansion, isothermal expansion. Here's the one molecule gas, here's a piston, right? And the piston has a weight that is perfectly tuned to balance the pressure of the one molecule gas. Right? You get the idea? And what we're going to do is just diminish that weight ever so slightly so that the imbalance of forces is just enough to push the piston up. Now, in this particular design is not great. This will actually be an important point for later. It's not great because as the piston rises, the pressure exerted by the gas drops. So we have to keep adjusting the weight there. That's a nuisance, and I'll just set it aside. Although remember that it's actually pulling. That's a nuisance. Now we can do some pretty quick calculations here. The pressure of the gas is given by the one molecule version of the ideal gas law, and the weight and the mass has to be balanced, has to be set so that it exactly balances the pressure of the gas. So you have two forces: pressure force going up and a weight force going down. At equilibrium, the two are going to balance exactly, right? And that then gives you the equilibrium height at which this thing is, the weight and the pressure just exactly balance. And that equilibrium height is given here by this formula. It's just, it's two lines of very simple mechanics, right? It's just kT divided by mg. That formula is going to come back in a moment, but that's the height, for that given mass m, that's the height at which the piston is in perfect balance with the pressure force going up. Now, correspondingly, we're going to be moving heat in. In the course of a twofold expansion, we'll have heat of kT log T going in, that's 0.69 kT, and it's going to be passed in ever so tiny increments. What's going to happen is the gas is at equilibrium, expands just a little bit, it momentarily cools off because of the expansion. You've drawn a bit of work out to lift the weight. Because it's cooled off, heat now passes in a tiny little increment into the gas, and then the process continues ever so slowly. Happens very, very slowly, and the slower you make it, the closer you get to the ideal case of thermodynamic reversibility when everything's in perfect balance. Okay, now that's the process that's imagined. This is entirely fantasy physics. Right? Now, to see that it's entirely fantasy physics, you just need to think about what fluctuations are doing. For, how heavy is a piston going to be if the collision with a single molecule is going to keep the thing up in the air? Right? We are clearly talking about an extremely light object, right? An object of molecular scale weight. So let's just look at the thermodynamics or the statistical mechanics of the piston by itself. If you just look at the piston by itself, you already see what the problem is going to be. The massive piston by itself is going to have, it will be canonically distributed in its various degrees of freedom. It will have various different energies of height. There will be a distribution over the different heights, which is just it's a Boltzmann distribution over height. I mean, Boltzmann, I've not read the original Boltzmann, but it always has his name on it, the Boltzmann height distribution. And so you end up with this probability distribution just over height, but you integrate out all the other factors. There's an exponential decay term here, and then there's a factor out the front. Now, any distribution will have statistical parameters. There will be a mean. The mean of this distribution is kt over mg, and that was, you might remember that was the formula I said this one matters. So merely by virtue of its own thermal energy, this piston is already at the equilibrium height without there being a molecule to talk to. So putting it another way, it's already talking with all the other degrees of freedom in the isothermal system, and that's already lifted the thing up quite independently of what's going on with that molecule. It really doesn't even know the molecule's there. Right? And then in terms of these statistics. And then the more important figure is the standard deviation. That tells you the spread. Right? And the spread of it turns out to be exactly the same number. It's a simple exponential distribution. Nothing terribly fancy here. And that turns out to be the same number. So factor that in. This is what the piston is doing by itself. Right? That's what the piston is doing independently of there being any molecule trapped underneath it. It's just bouncing around wildly and happily. And it's probably worth waiting because there's a lot more to come. And I know this is very sketchy, but it'll get more precise. Okay, so this then I claim is what's going to happen. You superimpose fluctuations, and I don't know, if there is any process there at all, it is so completely obscured by everything flapping around backwards and forwards. What about the heat transfer? You can again tell the same story. I'll do it fairly quickly. I was a little sneaky. I actually showed you how to do this calculation in talking about the Einstein stuff. We know that this molecule has a mean energy of 3/2 kT if it's a monatomic gas, right? And so therefore we know that its heat capacity is 3K over 2, and then we just apply Einstein's formula. I showed you how to do it, right? And now we know what the standard deviation of just the internal energy of this guy is, independently of anything else that's going on here. And of course, it's 1.22 kT. It's just this number here. I showed you the calculation. You do it very, very quickly. So at any moment, the fluctuations in the internal energy are vastly greater than any tiny amount of heat that you might be adding. Okay, so that's the template for what's going to come. Add in fluctuations, and you don't have a process because you don't have a beginning or an end. You can start set up the process any way you like initially, and it just goes all over the place. Right? I just mentioned here that the fact that you've got to keep adjusting the weight here is an external intervention that is actually bad. So there's another force field that you could use instead that wouldn't have that property. I did the calculation for that in one of the papers, and if you really want to see it, you'll find it there. But it's not a big deal. Now let's have a look at the claim in the Landauer Bennett tradition that it is possible to measure the state of something in a thermodynamically reversible process and ask what happens when you superimpose the presence of fluctuations onto that. Well, the short answer is exactly the same thing happens. It just gets messed up completely. So let me give you an example of that. This is the device that Bennett has proposed for detecting where the molecule is. So here's the chamber, and I think, can you just see that? That's the chamber. and the molecule is on one or other side, and we want to figure out which side it's on. The way we're going to do it is by slowly, this is meant to be a thermodynamically reversible process, slowly lowering this keel-shaped object down, right? And the keel is going to be tipped, right? And that tipping, because the pressure of the gas is going to shove up this side, but let that side fall, and the tipping of that keel is going to be used to identify the position, which is going to be recorded down here. So this is the key that records the result. So it starts out in the neutral position, and we're going to have an L or an R at the end here when the detection process is complete. So that's the first step. Now the second step is the key-shaped object is lifted so it can now slide to the left and to the right. Okay, no, I'm pointing out all these little steps you've got to do, right? Then the next thing that happens is you drop the keel down, you slowly, gently lower it onto the gas, it tips, and it moves the key over, right? And then you lower it down again and return, and there you go. You've now done your measurement. Well, I just want to say you've got exactly the same problem here in this system. If this keel-shaped device is light enough so that collisions with a single molecule are going to be sufficient to tip it, then it's a very light thermal system. It's going to have thermal energy of its own, and it's going to be rocking around wildly while this whole process goes through. And insofar as you can lock in any result here, the locking in is going to be completely random. You're going to, you'll just lock it in wherever it happened to be when you happen to twiddle the knob. If you're thinking there's a pattern to this, yes, it just keeps going like this. Right, so let's look at another example. Here's a scheme using ferromagnets. You want to measure the data bit down here. You have a reference bit whose state is going to be duplicated by this state down here. I created this animation, by the way, by carving up one of Bennett's diagrams. So I'll show you the diagram in a moment. But so you put this thing, you put this this little magnet through magnetic dipole through a field here that puts it into what he calls the soft state, and then it comes down here and responds to the state of the data bit, and then either points up or down according to what the data bit says. I'll show you the guy in. That's without the animation. But the basic idea is you're just bringing one magnetic dipole close to another, so that the one that's doing the reading then picks up the state. I mean, I would have thought it would point the other way, but arrows are conventional. I don't really mind. But it's got to be done in a thermodynamically reversible way, and that's the key thing. Right? It's got to be done in a thermodynamically reversible way. So I've made a slightly more stylized version here. This is the state that we want to detect. This is the detector. This is what we intend. We're going to slowly push it in. Thermodynamically reversible process means that all forces are going to balance perfectly, right? And then we're going to replicate the state of the data bit in the process of doing that. Now, the key thing to see about this is it's actually the same example again. This is just a compression of a phase space. To begin with, this dipole is in either up or down state, or it can move continuously, right? It's all the way through. And then as we bring the dipole in, we are compressing its phase space. So the thermodynamics of it is going to look exactly like the compression of a single component, like a one molecule gas. So I drew the picture here for you. It's just this is just the sequence of equilibrium states that make up that compression. And the key thing, and now I'm just going to claim this because this is a consequence of the theorem, the result I'll show you later. Theorem's too big a word. The key thing is that to compress that space, right? Spaces resist compression, right? There are entropic forces that want to keep the component through the whole space. They resist compression, so you have to push against it. The push that you apply has to be in perfect balance. The thing pushing, it's the key thing, the thing pushing is also a thermal system. There are no non-thermal systems, right? The thing pushing is also a thermal system. It will have its own fluctuations, just as the weight above the piston had its own fluctuations. Superimpose those fluctuations, and it's the same story again. You don't get that, you get this. Right? Everything just goes haywire. it just goes all over the place. All right, so
Can I?
you complement the graphics, perhaps?
No. I was wondering about the following. I mean, perhaps if I'm going back to Maxwell's original discussion of the demon, and you see, the point is that any attempt to derive something like the second law in a kinetic or statistical mechanical theory makes use of pictures of gases as consisting of molecules, and Boltzmann models them as hard spheres and tries to derive certain results from them. It is intended that all of this will apply to particles which are really, really small molecules. But actually nothing in the derivations depends on these particles being small. You could go through the same, look at the same equations for big particles. The same, of course, holds also for Gibbs. And indeed, as David Rotman mentioned, people are applying these types of reasonings for galaxies, where each molecule is...
Does it help if I jump ahead and say that the analysis I've applied here, I also apply to macroscopic systems? I'm not distinguishing. It's just going to be a matter of magnitude. It's not going to be a matter of qualitative effect. These effects happen at all scales.
I'm trying to help you see that. Maxwell himself has an explicit analogy. He says these particles in the box could be macroscopic.
Right.
And in fact, so he compares the demon to somebody who's operating a switch at the railway.
Oh, I see what you're saying.
If
the systems here were not tiny molecules, but they were stars in a galaxy subject to thermodynamic analysis, yes, I think the analysis would go through in the same way.
But there would not be an obstacle to something like the Smolakowski.
I don't think so. Why don't you just wait until the end, and then you can tell me if you think that's the case or not, because I haven't actually developed the guy yet. All right, so now the result. I need three notions that are going to go into it, and I'm going to go through these in turn, and then all the work is actually done in assembling these three notions, and then when that's done, getting the final result is, oh yeah, it's immediate. Okay, so first, the notion of an isothermal thermodynamic reversible process. I want to go through and make sure you know what that thing is. Then we're going to talk about, I'm interested in a subset that I'm calling self-contained, that I'll define for you. And then I'm going to go through very quickly, once again, how to compute fluctuations, because that's the key thing. These are all fluctuation phenomena. We just better be sure we know that we're doing this the right way. So let's look at a thermodynamically reversible process. You'll see how to generalize this very quickly. I'm always dealing with isothermal thermodynamically reversible processes, because that's the standard in the literature. You'd have to adjust things accordingly if you go to anything else, but I don't need to. So I have two systems in thermal contact at constant temperature T in a heat bath surrounded by T. Some process is going to happen. There will be some change in the state of system 1 and system 2, and the only interchange between those systems in the environment will be exchanges of heat. Okay? And that process, whatever it might be, is going to be one that is thermodynamically reversible. The condition for thermodynamic reversibility is that all thermodynamic forces are in perfect balance. Right? So that means all the temperature differences are either zero or so minutely removed from it that you don't care. It means all the forces, the generalized forces that push one way or another, are in perfect balance, or so close to it that you don't care anymore. And then you can derive this very quickly. It's so standard that I didn't put the calculation in. That arrow should only go that way. It's just getting carried away. The condition that this process be thermodynamically reversible is taken to be the condition that the total entropy of the universe remains constant, right? And that's equivalent to saying that the total generalized forces in the system are going to sorry. The total entropy in our idealized stripped down universe. Is that what's all yours? French?
Well, the universe is a synonym for system, right?
Yes. Yeah. In the total system, exactly. We think grandiosely.
Yes.
You know, when I'm concentrating on something, nothing else exists. Yeah. Right. And that's equivalent to saying that the total free energy is a constant for the process. Just a reminder of what these quantities are. The simple way to just see them all in one hit is to write down the first law for one of these guys. This D here is a process. It can just be a little differential, or it can be a differential operator, dd lambda, if lambda tracks the process. So the change of internal energy is the heat transferred minus. Now normally you would put in pressure times volume, PdV. You can generalize that if you have other magnitudes present to have an x dx, right? And the x is the generalized force, and the dx is the generalized displacement that goes with it, such that x dx is the rate at which work is being supplied. That's just the way the quantities are defined. I've defined free energy down here. Right? It's just oh god, did I get the sign wrong, Joss?
You're in good company.
Yeah, the sign's wrong.
I don't care.
Yeah, it's a wrong sign. It's a minus. Never mind.
Wait, shouldn't that generalized displacement be lambda if it's lambda the next line? So if the process parameter is lambda, then generalized displacement should be d lambda, right? Yeah,
when I work through it in more detail, you sort of bounce around. You then make dx d lambdas and things. But yes, yes, correct. If in fact, what I want in order to have just one process going on, what I'll do is I'll reparameterize that x so it becomes a lambda, and then technical details that really don't matter, but they're all written down. We can go through them if you really force me to. Okay, so let me just go through it. The condition that the total entropy of the only part of the universe we care about, our system, is constant, corresponds to these generalized forces vanishing. For example, opposing pressures balance perfectly. Opposing electrical forces would balance. The resistance of that dipole to be compressed is going to come out as a generalized force that is going to be perfectly balanced by whatever shoving the thing. And very importantly, that's equivalent to the constancy of the free energy. Okay, if you've never seen free energy before, let me tell you that really matters a lot. The constancy of entropy in a system, the total entropy in a system like this is equivalent to saying that the free energy of these two guys added together is constant, but forget about the environment. If you've done any physical chemistry, this is the condition that gets used endlessly. So it becomes, constant free energy is synonymous with thermodynamically reversible process. The calculations needed to do that are very short, and in my paper and in every thermodynamics textbook worth a damn. Okay, that's what the processes are. Because there is always lingering puzzlement over what they really are, let me just say what they aren't. It's just worth just saying it, because a thermodynamic process is not merely something that's very slow, right? Merely being very slow does not make you thermodynamically reversible. The classic counterexample I learned from Jost, who got it from Sommerfeld, that's only in the German edition, as far as I can tell. Yeah, which is interesting, because if you have a capacitor with which is charged up to a high voltage, right, a lot of work energy in there, right? If you discharge that through a resistor, you can discharge it as slowly as you like, but you are, no matter how slowly you do it, you are converting the work energy of the capacitor, it's a Leyden jar, into heat. Maybe that's exotic. Here's a much simpler example. Here's a balloon in a vacuum or in a lower pressure chamber. Just put a very, very tiny pinhole, and you can irreversibly expand the gas out to fill the room, and it can go as slowly as you want it to go. Right? You can go as slowly as you want it to go, but it is an irreversible process no matter how slowly it goes. The speed is the wrong thing to look at. It's the balance of forces that you have to look at. And the near perfect balance of forces is what makes things go slowly. right? So the slow speed is a consequence, not constitutive of the relation. Why use philosophers' talk? Here's another example. It's not merely processes that can go either way. I already talked about that before. So if you just home in and look at one part of a process, you can say, oh look, that can go either way equally easily. That's not enough. The example I've given here is the one that I talked about in the context of the Brownian computation. You have a gas that is confined to one side of a chamber, one molecule gas, release it, right, and out it goes, and then you notice that the reverse trajectory could equally happen. Right? So that doesn't make it reversible. Coming back to its initial state doesn't make it reversible. Right? Poincare recurrence. Right? Okay. All right. So now let me introduce. Is that okay? All right. Well, I'm looking for twitches. All right.
Twitching a lot. I'm holding questions. I don't want to stop you.
Yeah. Okay, I'll make a run for it at the end then. Okay. Now here's the next process. It is common in when we talk about thermodynamically reversible processes to include non-thermodynamic interventions, non-thermal systems intervening. Right? I already had an example of that. Right? So when we do the reversible expansion of the gas, that lifts up the way it's actually done is you have this pile of shot here, heavy lead shot, and and the hand of God reaches down and picks one off and picks one off and picks one off, and because this is theological, right? We do not ascribe thermal properties to this system. Now, as far as I can tell, that's perfectly fine, as long as you're trying to discern thermodynamic properties of this. Of this system. But if you're interested in understanding what is going on in the totality of the system, and you're interested in imagining what might be happening in a computer that actually sits on the desk here and is doing certain operations, to have a non-thermal component as an essential part of the operation is unrealistic, because there are no non-thermal components that you can build into the design of your computer that's going to be adjusting things. Any component will have its own thermal properties and will have to be included in the analysis. Right? So none of that external intervention. All right. Now the next thing that we don't want is we don't want to include thermal systems that are very far from equilibrium. In fact, so far from equilibrium that we've forgotten that they're thermal systems. Right. And so the example of that. So the example of that is the following. Here, I've been told, is a way that we can do a nice, slow, gentle, thermodynamically reversible compression of a one-molecule gas.
That's good for my question.
I'm sorry?
That's good for my question.
Oh, was it?
So I'm glad I told you.
Okay. Okay. All right. So here's the idea. You get a very, very massive object. I tried to make this look like concrete, right? And it's on wheels, and it glides ever so slowly, frictionlessly in, and while it's doing it, it is slowly compressing the gas, thermodynamically reversible process, so I'm told. Well, yes and no. As far as the gas is concerned, the gas is certainly passing through a sequence of equilibrium states. And as long as you do your inferences on that sequence of states and do the appropriate things, everything is going to be okay. But if you're considering the total system, if you're imagining you might have one of these inside your computer, then you have to consider the thermal properties of that very massive mass. Now, it has a thermal degree of freedom. It has a linear degree of freedom in that direction. And we know what it's, remember, a thermodynamically reversible process is a sequence of equilibrium states. So if this is the sort of thermodynamically self-contained, thermodynamically reversible process I'm talking about, then all the components have to be at or near thermodynamic equilibrium. Thermodynamic equilibrium for that mass, in that 1 degree of freedom, is a simple one-dimensional Boltzmann velocity distribution.
Okay, I'm getting very worried that this notion of everything being equilibrium is overly demanding. I mean, we can have systems with wildly different relaxation times, and we can say we can be operating timescales where for the component we want, we're inside the relaxation times. But other systems are. If we're not allowed to do that, then no computers can be made available for this diet.
Yeah, good point. I don't know what to say to that, but I think it's going to be a problem for any analysis of any thermodynamically reversible process.
So I'm going to guess my way of getting around it is I'm going to build my system using choosing my realization types carefully, so things are.
Well, just hold the thought. It might maybe there's a lot more to come. So I've got to get through it. Okay, so this is actually very far from at thermal equilibrium. Its mean velocity is 0, and it's fluctuating ever so slightly from side to side. And you can use the Einstein fluctuation formula to figure out exactly what its velocity is. But if this is any sort of massive object, it's going to be extremely tiny. So if it is moving univocally so that it can halve the volume of a gas there, it is very far from that equilibrium. And what you're having is a slowing down of this mass ever so slightly, moving it slightly more towards equilibrium. I'm not quite sure what it is, but it is not a thermodynamically reversible process that consists of a sequence of equilibrium states. Okay, how do we compute fluctuations? Well, once again, it was all there before. I showed you Einstein's way of doing it, and I gave it to you in Einstein's language. Now let me give it to you in a language that's compatible with the sort of stuff that you've heard from the other presenters. I'm going to first do the case that I don't need because it's now familiar, and then I'll do the case that I do need because it's a slight adjustment. So the case that that I don't need is the following. Let's look at an isolated microeconomically distributed system. This was the case that Einstein looked at. Remember, he had a gas in a chamber, and the gas molecules moving backwards and forwards. When there was a very slight, when there was a very improbable fluctuation, they would all end up over on one side. Okay, so the volume of phase space corresponding to the equilibrium system is this enormous volume here. And I don't remember who was saying it. If you calculate, how enormous that is, it really exhausts it. 99.999999999%, huge number. And then I'm sorry? Is that right? Yeah. Okay. So down here are the non-equilibrium states. And the system trajectory is then going to be wandering through, and we know from the microeconomical distribution that the probability that it's going to be in any one of these phase volumes V being the phase volume, is proportional to the volume itself. Okay, nothing shocking there. I thought nothing shocking there.
If it's ergodic.
Okay, this is the way Einstein did it. Yeah, sure. All right. If it's or if it's well behaved, shall we say? Right. Now the next move is then to give an equilibrium macroscopic description of the non-equilibrium state. Now I actually put some effort into talking about that because I wanted to use it again. And so why is it fair to say that the entropy goes with a logarithm of the volume? Well, part of it is it's a definition, but it's a definition that has a very pretty property. And that is that if we were to somehow capture that state, right, and make it into a little mini equilibrium state in its own right, then it would indeed have this as the ordinary equilibrium thermodynamic entropy. Right, so, for example, the gas momentarily fluctuates to one side. You trap it there and ask what its entropy is, and that formula will still work. And so that's really all there is to it. Now we just finish up. So combining those two equations, you get the entropy S is K log P, the probability plus a constant, because we have proportionalities up there. Turn the thing round the other way, and you get probability is proportional to the exponential of S over K, which is in fact the formula that Einstein uses in various places. This is the formula that he uses later on for the wave-particle duality calculation. He starts with that, I think does a power series expansion. Okay, but this is not the system that we want. This is an isolated microeconomically distributed system. It turns out, though, we can give the same analysis just by adjusting the formulae slightly for the case that we care about, merely by replacing entropy by free energy. All right, so that's the next thing. I can use the same picture, except now it isn't, in fact, possible for the trajectories to cross because we're looking at a part, at a subspace of the full phase space. But I didn't draw any crossings, but I have to redraw the damn thing, and I didn't want to do it. So instead of the microcanonical, we have a canonical distribution. So the probability that the system is at some point there with energy E is proportional to the exponential of E divided by KT. That's the canonical distribution. So what happens if we have some volume, right? Well, you're just going to integrate that factor over the volume, and that's in fact this partition integral here. So you pick some volume V, Z of V, Z of V is just the candidate Z of V is just the integral of that over this quantity here. We're now going to give that a macroscopic description in exactly the same spirit that the macroscopic equilibrium description in the same spirit that we had before. One of the standard relations in equilibrium Gibbsian thermodynamics is that the free energy is minus kT times the logarithm of the partition function. One of the most useful relations there. And so when you put all that together, you get that the free energy of the state represented by that volume is minus kT log P plus a constant. Turn it round, and you get the probability of the state is proportional to the exponential of minus the free energy over kT.
I just want to make sure I understand the logic of this. So we've got this thing that's bouncing around all over the phase space, and we're assuming that probability of finding any region at a given time is given by the canonical distribution.
Correct.
And we partitioned the successful phase space into these macro states. And the idea is that for each one of those macro states, there's a certain entropy and hence free energy that we could associate with it if it were a equilibrium state. Like we could if we could capture it in one of those non-equilibrium states and treat it like an equilibrium state, we say, okay, this is the entropy associated with this, and hence
this is the free energy. Yeah.
And we find then the relationship between the probability and that free energy is that.
Yeah.
Okay.
That's it. That's it.
All right.
You want to come up? You finish it off. All right. I think now I'm in a position. Yeah. It at last. I know it's been a build up, but. Now you'll be disappointed. You're saying that's all there is to it. Wow. Okay, so I'm interested in any isothermal reversible process, which is a sequence of equilibrium states, all right, that has an initial state, an end state, a final state, stages, I'm saying, maybe something in the middle, what the hell. And I'm going to use the parameter lambda to parameterize it. For example, the isothermal expansion of the gas. Lambda would then be the height of the piston above the floor of the cylinder. Right? So, but that's the general system. Now, what do we know about this? It's a self-contained isothermal reversible expansion. Sorry, self-contained is in there. So I'm just going to take the two results that we had earlier on and combine both of them. First, the process is thermodynamically reversible. That means that the free energy of each of these states is the same. Remember, that was constant free energy. Right? So the free energy of this, what I've actually done here is I've divided it up into chunks and sort of integrated over the chunks, but you can do it with densities as well. It's not going to make any difference. So the free energy is constant along the process. That just says this is a thermodynamically reversible process and a self-contained one. There is nothing funny business from outside. Second, now this is the next thing. Remember that fluctuations can always fling things around. Right? So if the process has maybe gotten this far, right, a fluctuation is perfectly able to fling it over to here, or to here, or to here, or to here. That's exactly what we saw with that piston going up and down. What's the formula for that? Well, we just had that earlier on. The probability that if you're, that if all of this is accessible to you, that you will get flung to those different stages is just given by this formula here. So the probability that the fluctuation will bring you to the initial state is proportional to exponential minus f of the initial state divided by kt. The probability that a fluctuation will take in the middle part is the same formula, and then the same formula. Okay. I'm hoping you can now fill in the last step, right? All of these free energies are the same, and the probabilities of being in the various stages are the same function of the free energies, right? So what do you end up with? You end up with the general result that the probability of being anywhere on the process is the same. And that's the no-go result. That's the no-go. So it's the generalization of what I showed you happening with that piston. It's saying that, in fact, if you do it just right, the probability distribution for the positions of the piston will be uniform over the heights. So it's, you know, sort of the worst case if you're trying to get any sort of process going. Yeah, more to come. I've got a bit to say.
Okay.
So let's make it quick because I want to finish before lunch because.
Oh,
You
this
might
is a
be
quick
able to-
question.
Okay.
So this is all to say that device you were showing earlier, when we go one direction or the other, it won't give us what we want because it'll just be going haywire.
Exactly. That would apply to that. That's an example of a thermodynamic class, a thermodynamic reversible process. It's uniformly distributed over the strings. All right. So let me keep going here. I've got another graphic I'll do quickly. So this is what you thought you were going to get: a nice slow process, and in fact, this is what you're getting. Okay, I know that's overkill. You got the idea. All right. Okay. So let's move on. So, but now there's actually more to be said, and the more to be said, I'm starting to think is more important than the no-go result. We actually want to be, you know, this is great, but now how do you build anything, right? If fluctuations mess up everything, how do you build something? You have to be able to beat fluctuations. So, question: what does it take to beat fluctuations so you can actually have a process go through from beginning to end, right? And this stuff matters, and it's worth talking about. The formulae tell you how to do it. It's very simple. You just need to have some sort of a gradient in the free energy, right?
That's what I was about to ask about.
Yeah. Okay. Yeah. Well, good. I'm glad you held it. So if you have the final state at a lower free energy, loosely speaking, an analog, a higher entropy, but you know, then you can drive the process forward. It's going to be probabilistic. It's always going to be probabilistic. Right, so what you can do is make it more and more probable that you bring the process to conclusion by making this final state have lower and lower free energy, but that's going to be dissipative and be creating entropy. So there's going to be a trade-off between the probability of getting the process to finish, right, and the amount of entropy that you're going to be creating. Right, so let's look at that. You'll release it from here, and then you're going to recapture it there. There's going to be a process where you start out with the thing in an equilibrium state. That's why you can use the free energy formula, as I said. Release it. It'll fall down the energy slope and get recaptured over here. I'm going to move a little faster because I really do want to finish. Because I've got nice pictures. Okay. So there it is. So when the process moves from the high free energy state to the low free energy state, you'll have a change of free energy of this amount, and that is translated directly into the net creation of total thermodynamic entropy in the total system that you're interested in. And you just divide the free energy by free energy change by t, stick a minus sign. So the free energy goes down, the entropy goes up. Right? The formula connecting them is very simple, quite standard. So you know, free energy changes as surrogates for entropy changes. Free energy decreases as surrogates for entropy increases. Now, this is in fact not the best way to do it. You want to do it in the least dissipative way possible, the way that creates the least entropy possible. And just having a slope like that is not good because the system can end up anywhere along here. So you're creating a lot of entropy in order to get it over here, but there's going to be a lot of occasions where it'll be there, and so you're in effect be wasting the entropy that you're trying to treasure. So here's how you do it. What's the best case if you want to get things to finish? Well, you've got to start somewhere. So here's your initial state with some free energy there. Here's the final state, which is in the lower free energy state. So probabilistically, you're going to end up here according to how deep you make the well. And then you just want to block out everything else as much as you can. So you put a big free energy mountain in between. Now, you don't make the mountain infinitely high or nothing can get over. You just make it high enough. And then it's just going to be a matter of time, because the higher the mountain, the slower the process is going to be. Crudely speaking, what you're waiting for is a random fluctuation to throw this system over the mountain and down to the other side. And the higher the mountain, the longer you have to wait. Right? But if you take that setup, then you get what I think is the formula for the minimal dissipation. So you release from there, recapture there, you release it from the thermodynamic state. That's why I can use the F formula and it means something. And then you recapture it in the other state, and it's going to be unlikely to be there. You just apply the formula that we had before. The rate, these are the probabilities of the final and the initial state, right? And they are going to be given by the exponential of the negative difference of free energies in this expression here, which then goes to the entropy using that earlier result. I should just make clear what the initial probability is. This is not the probability that you have set the system up in that initial state, because I don't know what that probability is. That's a matter of your psychology and funding. This is the probability that once the process is underway, the fluctuation is going to send it back to the initial state as opposed to the final state where you want it to go. Right? So we're going to turn that inside out, and we get that the entropy creation, it's a very simple formula. I'm very happy with it, and I'm sure it's been discovered many times before. The entropy creation is given by k log, the ratio of the probabilities. And I just note that those probabilities are odds ratios. What is the odds of finishing? Well, it's the probability of the final state divided by 1 minus the probability of the final state. And by the setup here, we're assuming all these intermediate states are improbable. Right? So very simple, very lovely formula. The amount of energy, so if you know the odds that you're prepared to live with for completion of the process, you can figure out how much entropy you're going to have to create. So let's do the formula. Let's get into the sums here. So let's start out on a molecular scale. Let's say that I'm willing to settle for a 20 to 1 odds of completion. In other words, there's a 95% chance that my process ends up where I want it to end up. Simple formula. The amount of entropy that I'll have to create is going to be k log 20, right, which is just 3k. Now that is for any process that has a definite beginning and a definite end. Any process at all. Right? This is not something fancy, but you remember in the measurement process, right, where that keel was going to be lowered down, that was the reversible process. Well, there were lots of other processes there. There was a process whereby you twisted a knob so that this key-shaped object would rise up. That's a thermodynamic reversible process. It'll be subject to fluctuations. If it's being carried out at the molecular scale, you will have to apply this result to it. Right? Every single step, no matter how silly, no matter how trivial, if you wanted to go from start to completion, right, you will be creating entropy. So the quantities of entropy that we're talking about here are simply going to be swamping anything that are being tracked by the Landauer principle. Okay, so at some point, I'm guessing about 95% of you have had this thought, but wait a minute, if he's right, that means there can't be macroscopic thermodynamic reversible processes. Yeah, that's right, there can't be. Right? But it's not that bad. So let's say that I want odds of completion to be some really big number. I just picked this at random, but odds of completion of 10 to the power of 10 is pretty good. That's a great deal better than the odds that I would give myself for my next driving home from here. I don't think they're that good. The amount of thermodynamic entropy that's created by the formula just comes out to be 25k. What is 25k? Let's try and get a grip on what that means. Well, 25 kT, which is an energy quantity of comparable magnitude, that's simply the mean thermal energy of 10 nitrogen molecules. Right? I just made a nitrogen because because I could a nice picture of nitrogen molecules here. So yeah, this is going to affect things on the macroscopic scale, but it's not going to make that much of a difference. Okay, let me try and pull it all together. I think I found what is probably the simplest, now that I think about it, toy example of this. I've stripped away absolutely everything to leave only what I take to be the barest components of the process, right? And it's the example of a bead on a wire, right? And if I think I can just get through that, there'll be a few minutes still for questions. So here's a system. This is I intend this to be a at least on one scale, a tabletop apparatus, right? So maybe it's about 1 meter wide. Here's a horizontal wire, and there's a bead that can slide frictionlessly along the wire, right? Usual sorts of idealizations. Now, each position that the bead can occupy on the wire is going to be an equilibrium position, right? Because all the forces are perfectly balanced. Well, there are no forces, so they're all perfectly balanced, right? So it's and so therefore the moving of the bead across the wire is going to be a thermodynamically reversible process. If we conceive of that as a sequence of equilibrium states, can you actually bring that about? Well, yeah, it's very, very simple. You just get under here and just sort of lift ever so slightly and just tilt the wire just a tiny weeny little bit, and then the bead is going to just slowly slide along. And there's your analog of a thermodynamically reversible process. It satisfies all the conditions that I've talked about. There just isn't very much there, so yes, it is completely trivial. But that's okay. Even this system, you've got a theorem. The theorem has to apply to even the trivial systems. All right, so I haven't said anything about fluctuations yet. Right? Remember that. But now we want to impose fluctuations onto the bead. It is a thermal system. What's the effect of thermal fluctuations? For a macroscopic bead of 5, I took 5 grams as a macroscopic bead. I didn't actually weigh any beads, but I assume beads might weigh 5 grams. Okay. All right. 25 degrees C, which normally would be a reasonable representation of ambient temperature, but over this past week has been a little low. And then using that just Maxwell velocity distribution, you figure out that the RMS velocity, a typical sort of velocity that it will have, is coming out at around 10 to the minus 9 meters per second. So there are thermal fluctuations that affect the bead, so the bead is just jiggling backwards and forwards ever so slightly, but you really aren't going to be worrying about them for all practical purposes at macroscopic scales. They are of the order of just little molecular jiggling, so it's not the sort of thing you would care about. But now, what happens if you go to the other extreme? And let's have a molecular scale bead. Now, I thought I'd pick something fairly big, just to make sure that I could have done a hydrogen atom. I chose an object of 100 atomic mass units, which turns out to be an N-heptane molecule. N-heptane is a component of gasoline, or can be a component of gasoline. Normal heptane, in other words, a straight chain, 7 carbon atoms in a row. And if you're thinking it's familiar, yes, it is the one that, by definition, has 0 octane on the octane rating for gasoline. Right? That doesn't mean if you buy gasoline of 0 octane, it will be N-heptane. It just means it will have the same anti-melt characteristics. Something you didn't want to know, that now you do. 25 degrees. The RMS velocity of that, root mean square velocity, is 157 meters per second. So the sorts of velocities that this would have were at 100 atomic mass unit bead, which is quite a big molecule. 7 carbon atoms and all the hydrogens around it. So if this is a meter-long thing, it's the fluctuations are really. Time scale is an issue. I know that's what you're thinking about. But the time scales when you get down to these molecular scales are very short, right? These fluctuations really do matter. Ultimately, the 5 gram bead in the fullness of time is going to move over the wire through fluctuations, right? But it's going to take a very long time, and for ordinary human considerations, it's not going to be an issue. But this is what I said earlier: the analysis applies all the way up. It's the same result. Okay, so what happens if we want to suppress fluctuations? You want to beat them, right? Using that formula that we had earlier on. Well, you overcome the fluctuations by tilting this thing up, and then you can get the thing to slide down the wire. It's not the most efficient way of doing it, but it's a kind of natural way of doing it. Okay, so how does it work out with the 2 cases? We're going to be working with a probability of the final state of 0.999. I really want to be sure that we get there. Temperature is 25 degrees C, and I've divided it up into 10 stages. So the initial stage is 1/10, and the final stage is 1/10, just so we have concrete numbers to work with, that you can sort of get some grip on. For the 5 gram bead, in order to get a 99.9% probability of completion as intended, right, you would need to move that up by 10 to the minus 18 radians. Now, I know you can understand, one complete guy is 2 pi radians, so 1 radian is about a sixth of that, so then there's a tenth of that, which is about how much, and then there's a tenth of that, and there's a... Okay, yes, it gets very, very small. In fact, you'll need to depress the end of the wire by something that is many orders of magnitude less than the size of a hydrogen atom. So it's really, so to overcome fluctuations, they're there, but to overcome them involves manipulations that are so tiny as to be, it's certainly a practical impossibility, I would have thought. Okay, but what about, it's roughly 10 to the minus 7 of the Bohr radius of an atom, I calculated. But what about the other case of the 100 atomic mass unit molecule? Well, it turns out, even if you tip the thing vertically, so you get the maximum case of pi on 2, right? In order to really hammer those fluctuations. I didn't show the numbers here because virtually nothing happens. You get virtually no control, whatever. And if you think about it, that's kind of plausible because N-heptane is a component of gasoline, which is a volatile gas, and it's entirely plausible that a volatile gas is going to evaporate. N-heptane can support a vapor above it. There will be an attenuation with height, but it's not going to be significant over the space of a meter. Now, I should mention that this is not the most efficient way of doing it. Remember, if you just have the slope that goes down, you still have the possibility of intermediate states coming about, right? And so, remember I said make all the intermediate states probabilistically inaccessible. So what would that look like with the bead on a wire? Well, that's what it looks like. You just bend the wire up, that's all. And so you now, in this case, are literally waiting for a random fluctuation to fling the bead over. I mean, you would get more interesting results if you look at intermediate sizes, somewhere between molecular and macroscopic, and then you can kind of get more fun things to play with. But since those aren't the cases that I'm directly associated.
Time travel is really a time scale, so really a natural in this case, I think.
Yes.
Just to give up the thermodynamics, making that from 10 kilometers high would be a good idea.
Yes. Yeah, make it the high like it. Just don't make it infinitely high, or it's not going to happen.
Don't make it light, high, if you really high to the answer.
Yeah. Okay, so there are other more complicated cases, and I would love to show you all the calculations because they get long and complicated really fast, and it's so enjoyable. But I know lunch is coming, so I'll just show you the pictures. So I wrote a paper that's got all this stuff laid out in detail. It's linked to from my website. And so I calculated 2 cases in some detail. Let's say you want to move a charge through a channel. Right? This is the sort of thing you want to do in computers. You want to move a charge from here to there. It's quite a basic operation. If you don't have anything pushing it, it won't go. How do you push it? You get an electric field in the channel. How much of an electric field do you need? You need enough of an electric field to overcome fluctuations. In the circuit theory talk, you need enough of an electric field to overcome thermal noise. What I'm talking about is for circuit theory, it's just noise, to overcome noise. And then I also calculated a much more complicated case. This is the properly worked out example, or as close as I could get to it, that Bennett showed us, that I think he originally got from Landauer. Here's a charge, and you want to measure whether it's positive or negative, so it's a binary measurement. The way you do it is you have this little gizmo here which has an electric dipole on it that can either be pointing this way or this way, and then you gradually let that approach, right? And its phase space gets compressed, and in the course of the compression you end up with the thing then reading the result. You then need to somehow have another process that will export the result, but that's just one phase of it. You need to do a compression, so you need to have a force that pushes it in. It turns out the system comes equipped with its own force. We tend to think that that there is no net attractive force, say, between a dipole and a charge, but there is a little residual force, and that's actually enough to power the whole process. And so what happens is that this guy will just automatically fall into a potential well if you do the sums, and the amount of entropy creation can then be figured out, and it turns out to be, you get some number, but it's certainly a great deal more than what Landauer was tracking. So let me just make some general results. Some general remarks they go right back to the beginning. There's been a program of research underway, certainly since the 1950s, that's trying to connect general notions of information, general concepts there, with the sort of stuff that was in books, I guess. I don't know. You get the idea. With entropy, heat work, thermodynamics, it's steam engines, right? It's something that a lot of people find viscerally very appealing. It's the sort of thing that I found viscerally appealing when I first started working on it. John Norton and I, sometime in the 1990s, got that book by Left and Rex on Maxwell's Demon, and we were really intrigued. We thought this was great. But we had this problem that we couldn't get any of the results to work. And then it gradually decayed, and we eventually realized that, at least in our view, they didn't work. I know it's tempting to say that, isn't this the sort of way things go with history of physics? Who would have thought mass is energy, that particles are waves, that geometry is gravity, right? Why can't information be entropy? Well, sometimes not every great idea works out, right? And so perhaps it's unkind, but my working hypothesis now is to put a very low prior in my basic moments on any proposal that tries to make this work. I've just sort of grown tired of seeing proposals that are supposed to have been done. Let me see if I put this up here. Yeah, so if you go to my website, oh, fancy that. If you go to my website and then click on this link here that says lectures, you'll get to this page. And then the first one at the top here says Foundation Statistical Development. And it'll be this. And you get the PowerPoint and the papers. And there's this guy, there's the PowerPoint and a few papers to read. The stuff that I've been talking about is pretty much summarized in this one called All Shook Up. But it sometimes gets a little brief because it's referring to stuff in other papers. That's it. Thank you, folks. Wayne, would you do me the favor of sort of fielding the questions? Because I see them here and here, and I'm just very bad at it, and I keep track.
Yeah, it's a very beautiful presentation of the search model of inferentialist computation, and I understand it now as I had previously, but in understanding it, I now feel deeply concerned that it's not sufficiently general to capture the kind of notion of computation.
Could you speak up just a bit?
It's not sufficiently general to capture the notion of computation that's supposed to be in play for Bennett et al. I mean, one way of seeing that is to say, look, if I've got one of these presumably very delicate micro-level machines that's supposed to do a calculation in a thermodynamic and reversible, whatever the relevant sense what it is, the last thing I want to do is to put it in thermal contact with a heat bath where there's a bullet rate. I mean, and so insofar as the notion of thermodynamic reversibility that's in play needs, I think this one does need, really can only be made sense of on the kind of assumptions I've got instantaneous equilibrium of components. But the conclusion I draw from that is that can't be the notion of thermodynamic reversibility that I had in mind. And I take it the notion is something more like this, that I can, I take my machine, I give it a clean input, it runs the calculation, take away the output, I give it a new clean input, I can keep doing that indefinitely often without dissipating heat to the environment. And that notion doesn't seem to be any requirement for bits in the machine that instantaneously thermalized.
I'm not telepathic, so I cannot read what's in the minds of Landauer and Bennett. I can only go on what they write. And universally, their writing is of equilibrium notions. and equilibrium processes. I mean, I quoted Bennett's, statement of the Landauer principle. He's very clear. He thinks these are thermodynamically reversible processes. Can I suggest that what you have sketched is the following? Maybe there's another research program that makes all of this work, but you're concluding that it has to be done with non-equilibrium systems. And that this is the place where something like the program that Landaur and Bennett have sketched out could be made to work. And I have nothing to say on that. I mean, I just don't know.
I can find out. Just the only quick thought exegesis in that case is, do they say at any point in that case that they want their computer itself to be a thermal equilibrium throughout its operation? Did they do like completely take it for it? But that seems a crazy thing.
I think it's presumed all the way. I think it's presumed all the way through. I guess I'd have to dig to find a quote. But if they don't mean that, I mean, they do keep talking about passing entropy to the environment for each step that they do. So I would be shocked if that isn't what they have in mind, and surprised if I couldn't find passages where they show that's what they do in mind. But I don't have chapter and verse.
I'll take it back, not for any actual state, that they won't explicitly say the computer is a thermal equilibrium.
Yeah, I think that's right, but that is more symptomatic of the fact that they are very poor on giving a thorough thermodynamic analysis of anything. The thermodynamics is done very incompletely, very hastily. I read to you canonical statements of the view simply because that's as good as it gets.
But I mean, I think you're acknowledging that this would not be a no-go result for that alternative research program that says, look, if you want to have a really efficient computer, isolate the damn thing from its environment. Don't have it in thermal contact with everything, and have at best very regulated heat exchange from the environment.
Well, even then, look, I can't predict what sorts of results that you'd get out. But I would worry about the following. Thermal noise is very hard to get rid of. So let's just imagine that you have one of these computers that you're trying to set up to be free of noise. It's going to have many components. These are all going to be highly metastable systems. You might at T0 have them exactly free of that. But we're going to see some sort of thermal evolution if it's a complicated system. If it's only one component, or two components, in space at absolute zero with nothing else around, sure, it'll work. But if you have the sorts of complicated computers that we're talking about here, then any one component is going to be sitting in the environment of many other components. You might start it off at far from equilibrium. I don't know if it will stay there. It's now a matter of, well, this is now the problem that I guess we've been spending days and days talking about.
Yes, maybe.
Well,
oh wait, is there one over here?
Yeah, Nick had a question. I saw two hands to begin with, so.
Okay.
It's slightly quite quick. I think it's a less profound version of David's question, in fact. But earlier on, when you were talking about the Brownian Turing machine, you said you were happy to accept the idea that the final state would get trapped.
Yes.
If that's the case, I'm a bit puzzled about why what you call the odds was the relevant probability for thinking about whether this process was going to work. Because the chance your process completes, if you trap it when it gets to the final point, is going to be 1 if you wait long enough. And the odds you had calculated...
Oh, no, it's the same sort of probabilistic trap. It's exactly the same setup. What you do is you decide what the odds of completion are that you want, and then you make the free energy pit deep enough so you get that. There's no way to have an absolute certainty of trapping.
So trapping is not magic. It's not something you take for granted.
No. The trapping is itself a thermal process, and no matter how deep you make the free energy pit that the system is going to fall into, there's always some tiny probability of a fluctuation flinging it out again. You just make the thing deep enough so that probability becomes, at a level that no longer troubles you.
Okay.
Yes.
Well, this might be a long question or remark, but I want to really stress that, I mean, I mentioned the ergodic hypothesis, and you might think that it's just some technical detail, but I think it's really at the heart of where your approach and that of your opponents starts to diverge?
No, on the contrary, we both need it.
I don't think
Because
so.
without that, I don't see...
Can I ask my question? So here's the distinction. On the one hand, you have people like Boltzmann and Einstein following him, who think that what really matters in the statistical approach is how much time the state of the system spends in various parts of phase space. On the other hand, there is Gibbs, and in particular, even more explicit, people like James and Tolman, who think that what really matters is just some probability of phase space, which represents what we know about the system. When do these two things come apart very clearly? That's precisely when it happens that the energy hypersurface, say, falls apart in two disconnected regions. So that if the state of the system is in one part, it will stay there, or if it is in the other part, it will stay there. This is exactly what happens if you have a chamber divided into two parts. Okay. Now, it's very clear that in those cases, time averages will not be the same as probabilities as computed by microeconomical distribution, because these two things have probability 1/2. And if I'm Tolman or James, I say the mere fact that I know that the energy of the system is E entitles me to give probability 1/2 to one region and probability 1/2 to the other region. And those probabilities get into the Gibbs canonical or microeconomical entropy. Of course, if I'm Boltzmann or Einstein, I would have to say, no, it's only one part of the energy hypersurface that's accessible to the system. And so I'm restricting the volume to that part of the energy hypersurface. And therefore, time average for finding the system on the other part is 0. It doesn't matter whether I don't know about it. The time averages, the probabilities that I'm going to compute in my form of thermodynamic, representative of thermodynamical entropy, is going to be restricted to that. It's going to be different. Same thing applies if we talk about fluctuations. According to Boltzmann and Einstein approach, fluctuations are things that happen in the course of time to a single system. In the approach of Tolman and James and anybody who uses statistical mechanics in an inferential way, it's merely a variation across an ensemble, or it's an uncertainty in our knowledge. It doesn't have any application or any implication, I should say, towards how fast or how jiggly motions are in the course of time. And so, in the case of the Szilard engine, if I were one of those subjectivists or Tolman, the mere fact that I don't know where the particle is located would, and I use the entire energy hypersurface, even though it's disconnected in two parts, in false particles, would still give me the correct formula for the thermodynamical entropy. And for you, it wouldn't. So I think that that's really the thing that drives, or at least one of the fundamental points where those two approaches start to diverge. And as I understand you rather state that using the accessible region of the phase space is what is needed to do the correct thing. Right, and I'm sure you appreciate that that's a good point. But I think you need to realize that the other guys do not accept that as the only correct formulation.
Yeah, sure. They're wrong. So, I really worked hard on this. The key thing. So you made 2 points. So let me go through the first one. I just disagree with them because it's something I spent a lot of time trying to figure out. It is essential for the Landauer Bennett people that the entropy changes that they're tracking, right, have to go with heat. Right? They take entropy and heat to be synonymous. In some versions of the Landauer principle that you'll find in the elevated literature, they don't even talk about entropy. They only talk about heat because they're nervous about entropy, so they talk about just the passing of heat. And so I looked very carefully into the way you make that connection between the P log P formula, right, and the Clausius dq reversible on T. And if you don't have that accessibility, now I don't want to make any grandiose claims about all of thermodynamics. I just want to make the one narrow claim. That PDP doesn't connect up with Clausius unless you have the system exploring the accessible phase space. That's the first thing. Now, the second thing is the fluctuations that I'm talking about are real physical processes. That's why I went through all of the examples. And I fully believe, I don't think when you have that piston bouncing up and down, that it's simply a matter of ignorance as to where the piston is. Right? That the piston is actually moving very, very slowly. We just don't know it. Right? It's genuine. You can go back to the basic dynamics, and you can see that there's going to be a clear, if informal, dynamical story that you can tell. That every time it gets the sudden impulse of a single molecule, it's going to be flying up and flying down. So I'm sure it's a real process. Things wildly moving about. And I'm also confident that this is the correct way to calculate what those wild fluctuations are.
When you're showing the inversion in just a multi-time correlation function.
I'm sorry about that. Okay.
Well, I'm perhaps less confident than you are that there is only one single correct way to go about this type of topic. But I certainly, that doesn't mean that I disagree with you.
I'm following up on what Joe said is, I'm not saying that Landauer and Bennett do this, but if you were to, take a purely inferential view of all this, so all these, think of all these probabilities as epistemic, and take seriously the idea that what happens when energy is dissipated is it's passing from the variables that I know about to variables that I don't, and that's where the distinct heat work is. It seems to me that you ought to be able, in that connection, get the connection between P log P regarded as epistemic and heat regarded as epistemic. And then the relevant part of the phase space is not the part of the phase space physically accessible to the system, but epistemically possible because I don't know it's not in there, which is I think what you used to.
You're not giving me a hunch. You hope it would work.
What's that?
You're saying you hope you could.
Did I say that? I have a hunch it could all be made to work.
I have the opposite hunch.
Okay.
Having spent a fair bit of time calculating it, but maybe I shouldn't be too confident. But I'm more confident than.
That's one.
I mean, seriously, look. If you really want to pick up on this, this is the Eaters of the Lotus paper, which was published in a very good journal by an editor who gave me hell, if I remember correctly.
We do need to break for lunch. Is this going to be quick?
Yeah, just perhaps a quick illustration, I think, from the perspective of this framework, from premise that I think John was behind, but just to see why, if you're coming from this informationist starting point, knowing that the particle is on one side or the other of the box doesn't let you get any work out if the resource available to you is just modifying the location of a parameter and allowing it to move. So if I know that the particle is on one side or other of the partition, and I know which side it is, of course I can get work out. If I know it's on one side or the other of the partition, and among my toolkit is included the ability to measure which side it's on, likewise I can get work out. If the only thing in my toolkit is the ability to move the partition from left to right or right to left, then I can't get any work out on average. And again, you can do the calculation there relatively explicitly. There'll be a 50% chance it's on the right side and I'll get some work out. There'll be a 50% chance it's on the wrong side and I'll get some work in. And I'm not an average able to get something out. I take it that's likewise mathematically uncontroversial. The controversy is about where the input assumptions are coming in.
Yeah, I'm sort of, we need to go to lunch. Okay, yeah.
Thanks, John.